See, I give a heads up with a whistle. That feels like it can't have been very scary. Although maybe you thought you got a notification and then got surprised, looking around for the notification until you realize it was me. I've been here the whole time. for those who get the reference. Let's do our standard. I almost shit my pants. That's very severe for a whistle. Oh no. Maybe I've done worse. Yeah, game changer reference. This time we have something. I assume you can hear me, otherwise you wouldn't be replying. But this time we have something to test, which is we have to test that you can also hear the audio from my computer, because otherwise we can't really. I can claim that I've successfully accomplished the task, and you would not be able to check whether or not I have done so. Let's see. So, in the interest of the stream, how about we play some noise? Let's go with some. Let's do some Brownian noise. Yeah, let's do Brownian noise. Okay, so I'm going to start playing some Brownian noise just from Wikipedia. See if you can hear it. I've set it low initially, so it hopefully should not blow your speakers. Let's see. So how's the volume of that, and how's the volume on it compared to my voice? That's the thing we're trying to figure out. Okay, you hear it. That's good. Now the question is, volume-wise, do we want to have it louder or less loud? It's good as it is. Like this is fine. And you can still hear me if I talk over it. Quite low but audible. Okay, that sounds a little low. Some people want it a little lower and some people think it's too low. Okay, that sounds like it's good. If people complain that it's too loud and too quiet. It sounds like background noise. I mean, it is kind of like a fan in the background. All right, let me make it slightly louder. I'll nudge it up to here. Let's see. How about now? Okay. Okay. How's that? Is that better? Worse? The same? Perfect. Okay, great. Let's see. Let's see what we got here. And then I suppose we should check if you can see me as well, huh? So if I do this, you should see my face. Maybe. If I haven't completely messed up. Yes? Yes? Face? Face? The noise was almost as loud as me. That's great. You can see me. Okay, great. But you cannot see my screen yet. Face? Face. Okay, good. Everyone's confirming face with face. I like that. Can they copyright brown and white noise? I don't think so. Although I'm sure the YouTube copyright thing is going to ding me from using an audio file it recognized from somewhere. Face and alpaca. Oh yeah, alpaca, and there's also a little bee. Just for fun. And then there's a stack of rust crabs. The Ferrises back here. Ferrises. And then YouTube being happy with me because of all of you all. You can see the screen through my glasses. Oh no. Oh no. Oh, the overlay alpaca. Yes, there's also an overlay alpaca, which is there. I forget how I flipped this on OBS. It's on one of them. It's unclear. I have two channels. I have this one, and then I have an MIT class called Missing Semester that I also ran. Your left, right. Okay, great. My left is this side. That's my left. Okay, so this side, the alpaca is over here. Great. So we have Jay over here, and then we have those things over there. Perfect. Okay. So then let's see if we can get the screen on here. If I do this, you should see the screen. You should see my face in the top right corner of the screen. Alpaca on the mic. That's really what I should do, is I should align Jay so Jay sits right on top of the mic. That's pretty great. But you should see my screen. You should see a blank Firefox tab. Everything is working. Oh boy. That's pretty exciting. Everything working first try. Oh man. That means something's going to go wrong later. You just know it. Let's see. We're almost at time too. Perfect timing this time. It's working! Don't jinx it. It's too late. I've already jinxed it. All right. Oh, let's see. And then I will go back to this one. Back to my face for the start. Stream immediately crashes. Let's hope not. I'm talking to Jay. So all of my commentary is to Jay, and Jay is relaying the chat to me in person, like speaking directly at me. Okay, I think, oh, right, we have a full like 30 seconds before we have to start. That's amazing. I'm early for once. Let's see, let's get some order over here. Get this out of the way. This out of the way. All right. And then I need this guy and this guy. This can move over here. All right. It is 6 p.m. my time, which means in theory it's 4 p.m. UTC, which in theory is the time I announced. So I think we should get started. Let me do this. Hi everyone, welcome back to another Rust stream. This is going to be another impl Rust stream. It's very exciting. We've done some of these, over the past couple of months, but the most recent ones have been sort of agentic coding, either partially or fully, like the very last one. And then before that, we had the Billion Rows challenge in Rust, which is a little bit of a weird one because it was not really about idiomatic Rust in any way. It was like, let's see how much we can squeeze out of this by pulling as many tricks as we can. But this is one where I don't want to say we're going back to basics because that's not quite true, but we're going back a little bit to sort of where the spirit of the channel started, which was a combination of build things that I need for other reasons. That's not what this is. And build things for us to learn about protocols and learn about, bit patterns and learn about like stuff in the world through programming. That's very much where this started. It was like, when we implement TCP from scratch, it's not because we actually need a full TCP implementation. It's because we're looking to learn more about TCP by implementing the underlying thing. And so that's what I want to do again today. I want to take the time to essentially sit down and implement audio noise generation. So let's, if I switch over to the screen here, you'll see on Wikipedia, there's an article on the colors of noise. And I know some people will be annoyed with me, so I'll switch it to dark. I'll do the same here because I don't think it does it. Oh, there we go. So it turns out the audio noise actually has multiple different colors. And you might have heard this, like you might have heard white noise, and you might go, well, what other kinds of noise are there? Well, there are other types of noise. So white noise is the one we're most commonly used to, but there are other types like pink noise, brown noise, blue noise. This is even, I liked when I just like randomly scrolled down this earlier. There's also, there's velvet noise, but there's black noise, also known as silence, which, that's a terrifying image. So I just figured, okay, I want to know what these are. Like, I know a little bit about audio, like theory, but not very much. But I do know that like white noise sounds different from pink noise, sounds different from brown noise. And so let's figure out what that is, and hopefully learn something in the process. But in order to implement noise, we also need to be able to generate actual audio that we can play back. You can't just like listen to noise without having some representation of that noise. And so I figured, what's the simplest possible audio format that we could implement ourselves? And I think that's WAV files. So WAV files, also known as WAV, or I guess it's waveform audio file format. That's not short for WAV. Unclear why. I guess they just shortened the first word instead of making it an acronym. Otherwise, it would be a WAV file, which I guess sounds worse than WAV. Which is a very old file format, and I'm hoping that it's old and therefore relatively simple, although that doesn't always hold up. But the other thing that's important about WAV files is that they are uncompressed audio. So MP3 files, for example, have a bunch of audio compression techniques in there to make the file smaller. And those things are all interesting, but I don't want to also try to learn all of those live during stream. And so instead, we're going to pick something that's relatively simple. And so this is a PCM format, which means that it's pulse code modulation, which is one of the simplest audio representations. And we'll get into that later, and I don't know very much about it, so I will also learn with you. But the intent here is that we should write a Rust program that takes a parameter that tells us the color of the noise. We should generate a WAV file with noise of that color. And maybe we let you configure the volume or something of that noise. And then we produce the file on disk, and then we can play it back, and hopefully it sounds similar to what the noise is supposed to sound like. I don't know. I think we will find out. Now, my one worry about WAV formats is that because it's an older format, with these older formats, you also ended up with like weird like container formats, and like everything was a little odd. So we'll see whether this ends up actually being a pain to implement, but I hope not. And this is a Windows, Microsoft format, but it plays fine on Linux. There's nothing Microsoft really specific about it. But we will find out. Again, I also don't know very much about WAV, but I have the impression that it's similar to, for images, you have BMP files, and BMP, like bitmap files, are almost just like you print out the bytes for the red, green, and blue value of a pixel, and you just dump those into the file one by one by one by one for every pixel, and then the resulting thing is your image. And so it's like very easy to encode back and forth from sort of a pixel representation to the on-disk version. I'm hoping WAV files are roughly similar. So let's dig in, let's find out. But I think first we need to hear what these noise colors sound like. And so if we go back to colors of noise here on Wikipedia, gotta always love Wikipedia, you'll see technical definitions of noise. And I skimmed this earlier. Yeah, here. The color names for these different types of sound are derived from a loose analogy between the spectrum of frequencies of sound waves present in the sound and the equivalent spectrum of light wave frequencies. That is, if the sound wave pattern of blue noise were translated into light waves, the resulting light would be blue, and so on. So if we look at one of these diagrams, so this is on the x-axis, there's frequency, and on the y-axis, there's intensity. So basically volume. It's not quite volume, but basically. And so this tells you that the intensity, the intensity is the right word, I guess, but think volume of the frequency, audio frequencies at 100 hertz, which is sort of a relatively low, like rumbling sound, like bassy sound, is the same as how intense the higher frequency sounds are, right? So up here we have, I'm guessing this is around 40,000 kilohertz. Sorry, 40,000 hertz, so 40 kilohertz. And that one you see has the same intensity. So the idea is that you get you get equally loud all of the frequencies in the sound. And if we play it back, it sounds like this. And so if you listen carefully, you'll hear that there's you hear quite a lot of high frequency sounds in there. And that's because there's a lot of high frequency in here as well. If you think about it from 100 hertz to 40,000 hertz, like if we equally distribute the intensity across there are way more of the higher frequencies than there are of the lower ones, right? Because as you go higher in the frequency space, like the frequency space is like a logarithmic space. And so the higher integrity one, or the higher frequency ones, there are more of. Whereas if we play, for example, a Brownian noise that has way more of the lower or more intensity in the lower frequency ones, it sounds much less sharp in a way. So you hear that this is Brownian noise. This is much more intensity in the bass and much less in the sharps. And then pink noise is somewhere in between, so you see it also decreases over the course of the frequencies, so it should sound somewhere in between, hopefully. Okay, so now we've heard the different noises, and again, the thinking here is that we should be able to produce files where the sort of audio spectrum of them looks something like this. And we can open the files in like Audacity or something to, which is an audio editing software, to try to see whether they actually look like this. But even just by playing it back, hopefully we can go like when we play our white noise, does it sound roughly like this? So let's find out. So for WAV files, let's dig into it from the beginning. The WAV file is an instance of a resource interchange file format defined by IBM Microsoft. The RIF format acts as a wrapper for various audio coding formats. The WAV file can contain compressed audio. We don't want that. The most common WAV audio format is uncompressed audio in the linear pulse code modulation format. Also the standard audio coding format for audio CDs. Nice, we're basically implementing audio CDs at the same time. Sampled at 44.1 kilohertz with 16 bits per sample. So this is useful. This is stuff I roughly know what is. So the 16 bits per sample is for every sample you take of the audio signal, how many bits do you use to represent that measurement? And then the sampling rate here is how frequently do you take samples of the sound? And roughly what we're going to do is, let's say we did 44.1, 44.1 thousand times per second, we're going to sample the current intensity of sound, like the movement in the air effectively. And whenever we do, we're going to store how much movement there was using 16 bits. And then we will do it again, 1 divided by 44.1 kilohertz later, and then we'll keep doing that. And what we end up with is a spectrum of time on the x-axis and intensity on the y-axis. And what we need to turn that into is we need to turn that into frequency and intensity, which you can do with a fast Fourier transform. We'll get there. Now, the reason this number is 44.1 is, I need to pull back like my older data representation stuff, but I believe it's because human hearing goes up to 20-ish, 22-ish kilohertz. That's like the highest frequency sound we can hear. And there's something called I'm going to get bitten by this, isn't it? The Shannon information theorem. It's something like that, but it's there's like a rule, basically. There's a rule that tells you that if you want to sample things, then you can perfectly reconstruct the underlying audio signal if you have samples at more than twice the rate of the underlying frequencies. So if you want to capture frequencies up to 22 kilohertz, you would need to sample at least 44 kilohertz. The Nyquist frequency. Yeah, Nyquist-Shannon frequency. I feel like we should be easily able to find this, right? If we go back to 44.1, yes. The selection of the sample rate was based primarily on the need to reproduce the audible frequency range of 20 to 20,000 kilohertz. The Nyquist-Shannon sampling theorem states that a sampling rate of more than twice the maximum frequency of the signal to be recorded is needed, resulting in a required rate of greater than 40 kilohertz. The exact sampling rate of 44.1 was inherited from PCM adapters, which was the most affordable way to transfer data. Interesting. The rate was chosen following debate between manufacturers. Why? Interesting. Oh, because it has to relate to like NTSC for TV and stuff. All right, well, regardless, what this tells us is we can choose any sampling rate we want for the audio files that we produce, as long as we put in the file what the sampling rate is. But if we want to produce sort of standard audio, we should probably produce 44.1 kilohertz samples. So that many samples per second with 16 bits per sample. And we should store it as 2-channel LPCM. We could probably store it as mono. That's probably also fine. Since LPCM is uncompressed and retains all of the samples of an audio track, professional users or audio experts may use the WAV format. Sure. Yeah, we'll call ourselves professional users and audio experts. That's why we chose WAV. Okay, we don't care about compression. File specification. A RIF file is a tagged file format. So there's a specific container format, a chunk with a header that includes a 4-character tag, and the size of the chunk. The tag specifies how the data within the chunk should be interpreted, and there are several standard 4CC tags. Tags consisting of all capital letters are reserved tags. The outermost chunk of a RIF, okay, so they can be nested, I guess, has the RIF tag. The first 4 bytes of chunk data are additional 4CC. The first 4 bytes of the chunk data are an additional 4CC tag that specify the form type and are followed by a sequence of subchunks. In the case of a WAV file, the additional tag is WAV. Okay, so let's we gotta dev streams. Cargo new bin. Feel like there's something here. Wave noise. It's like crush. What if it was wave as in ocean wave and it makes noise when the waves crash? What's the name of when a wave actually crashes? It's just called crashing. Like when the top of the wave turns white and it folds over. That has a name. Is it crest? No. Is it? Is it wake? Crest? I feel like it has a, there's a wave, crest, wake. The Kelvin wake pattern. Ooh, no, we're going to get distracted. Chat is very, are debating with themselves between wake, crest, and break. A tsunami is not, no. That's different. It can probably be used interchangeably, right? Like crest and no, because a wave is what you get behind a wake, I mean, is what you get behind a boat. I think it's crest. Wave crests. Aha. No, the crest is just the highest point of a wave. So arguably we should be trough because we're the bottom part of a wave because we haven't implemented it yet. Sure, why not? Great, let's do that. We're calling this tool trough because it's at the bottom of a wave because we haven't started implementing wave yet. Perfect. Okay, so what we're gonna do, there's an interesting question here also about whether we should make this print to standard out. I'm a little tempted to do so. So IO stood out. No, I need, oops, yeah. And then I'm gonna do out is out.lock. And then we're going to do write, this has to be mute, write to out. It said first you need to write RIF, right? First 4 bytes of the chunk data are an additional 4CC tag that specify the form type and are followed by a sequence of subchunks. Yeah, but do we need to give the length of the chunk as well? Because it said, and the size, number of bytes of the chunk. So we need to know the size of the file. We need to know the size of the file before we start writing it. This feels unfortunate. Sorry, I just need to open a window to get air in here. There we Maybe the top level is special. I wonder if there's a... I guess we will find out. First 4 bytes of chunk data. I think we're going to need to put a number in there. But let's do number of bytes of the chunk. So let's do 4. What's the network ordering of RIF? I feel like I want the RIF RFC. Let's see. Here we go. Oh, AVI files. Good old AVI files. Yeah, all chunks have the following format. 4 bytes is an ASCII identifier. 4 bytes is an unsigned little endian 32-bit integer. Okay, so we have a unsigned 32-bit integer, little endian. And then we'll use std.io write. What? Why can't I write bytes? Why doesn't it let me write bytes? All right, fine. We'll do this then. Out.write. Now, the interesting thing here is going to be whether this length of 4. Actually, let's be good citizens here and say result std.io error. Whether when you have subchunks, whether this length needs to be the length of, like, the combined length of all the subchunks, or whether it can just be the length of the first subchunk. I guess we'll find out. It's fine. Write all. But write normal. So the write just calls the system call for writing bytes, and that doesn't guarantee that it writes all of the bytes. Is you need to just write all, which might result in multiple system calls outgoing. Arguably, we could use a buffered writer here, but I'm gonna skip that for now. We can easily change that at the top later. Okay, so if we go back, we have WAV. The remainder of the RIF data is a sequence of chunks describing the audio information. The advantage of a tagged file format is the format can be extended later. Yeah, that's fine. Info chunks. The chunk may include information such as the title of the work, author, creation date, and so on. Okay, that's fine. There's a CSET chunk to specify the country code. Okay, I don't care about that either. A junk filler chunk. Oh, I see. So you can delete something just by changing that. Interesting. Okay. So top level definition of WAV file is a RIF with WAV, which has the format of the file, a fact chunk, cue points, playlist, associated data list, and WAV data. Okay, so this should be pretty straightforward for us because I think we can skip many of these. Okay, so the format chunk just... Oh, it's a format chunk. Interesting. That includes information such as the sample encoding, the number of bits per channel. So this actually means that we're going to have to write this out. We're either going to have to write it out to a file and then replace just these values at the end. So basically update the file after we've written everything out and know the length of things. Or we write it out to a vector and then we write everything out at the end. Mm. Okay, I think maybe then we will write this to a file and then we'll just patch the file at the end to inject the lengths. I think that's what we're going to do. So that changes this a little. So we'll do file create audio.wav. This is obviously something we're going to have to make customizable later. We'll make that this. And then this we're going to set to 0. And so now this is going to be a wave chunk, which is also going to be set to 0. And then we're going to have another chunk, and this chunk is going to be the format chunk, which we don't know what the possible option. I want the actual spec rather than the Wikipedia page here. If I can find it. Aha. Oof. The WAV specification from 1991. Oh, broken link. Aha. Pages 56 to 65. Now we're talking. Long PDFs. That's how you know it's an old spec and is a spec. 52. Oh, this is basically also MIDI. Nice. Okay. Yep. 50. RTF files. There's all sorts of things defined in here. That's great. Okay. This section describes the wave format. It's used to represent digitized sound. The wave format is defined as follows. Program must expect and ignore any unknown chunks encountered, as with all riff forms. However, format check must always occur before the wave data, and both of these chunks are mandatory in a wave file. Okay, so it's a riff with a wave with a format chunk. The wave format chunk specifies the format of the wave data. The format chunk is defined as follows. Oh, so this one is not tagged. Interesting. That makes me wonder if actually there's no length to the wave chunk either. Here, if we go to riff tagged format. I just want to see, here we go. Basic building block of a riff file is called a chunk. Using C to chunk can be defined as follows. Okay. Yeah, so you have a 4-byte character code. So it contains a chunk ID, which is a 4cc, a chunk size, which is also a long, and then it has data of that length. That's fine. This we know. We can represent a chunk with the following notation: CKID paren CK data. Okay, what's form type here? The first D word of chunk data is a 4-character form. First D word of the chunk data in the riff chunk is a 4-character code value identifying the data representation, right? So this would be wave. Following the form type is a series of subchunks. Which subchunks are present depend on the form type. Okay, but do the subchunks have lengths? Is what I want to know. So yeah, so this notation means it has this chunk ID and a data length and data. Yeah, okay. So whenever we see this syntax, but I see. So these are then strictly following each other. So it would be this 4cc and then, but this would be a, how can a 4cc be 3 letters? Like what happens if a CKAD is shorter than 4? Aha, padded on the right with blank characters, ASCII character value 32. ASCII character value 32? Why 32? Oh, space. I'm thinking of, I was like, isn't space 20? But no, space is 20 in hex, not in decimal. Okay. Interesting. So if we now go back down. Oh no. Oh no. I love specs like this. Great. So we need to remember that H's mean hex. No modifier 16-bit. C, I guess, is 8 for character. Okay, so this is a 16-bit by default unless you say long. So it follows sort of C convention. Great. Strings, Z is null terminated. B and W have size prefixes. Oh boy. Okay, great. I think that's most of what we need. Let's now go back to our WAV file. So we're going to have 4 literal characters WAV followed by a format chunk. The format chunk is defined as format. Okay, so this is that same notation. So there's no data length between WAV and this, but this now says format padded by space followed by common fields and then format specific fields. Common fields is a struct. Aha. Okay. So we will do repr C on this and padded. No, so packed, I mean. And we're going to have what exactly? We're going to have a format tag, which is going to be a word. So it's going to be a U36. Sorry, what am I saying? I said U36, wrote U32, and meant U16. And a channels, also a U16. And a samples per second, which is a U32. And a average bytes per second, also a U32. And a block align, which is a U16. And we'll call this the format chunk common. And then we will do, so this does need to have the length. So this will write out std mem size of format chunk common. This is going to return a U size. So we're going to have to cast that to a U32. 2 LE bytes, right? Because that's the size of a format chunk. And then we will have to write out the actual format chunk, which is going to be, we're going to do here a format chunk common. Now let's see what the format tags are. A number indicating the WAV format category of the file. You must register any new WAV format category. See, registering multi. Okay, overview of the multi. See, For information on registering, I don't want to register. WAV format category following this section lists the currently defined one. WAV format PCM. Great. Okay, so we'll do this. And then we can actually go in further. We can take this whole thing if we want to be slightly more... Oh, this selecting this PDF is broken. Okay, so we can do even better. We can say... repr, this is going to be a U16, and it's going to be an enum of WAV format category. This will be WAV format PCM, and it'll be equal to this. We can even give it nice docs. And then we can say format tag here is going to be WAV format category. And then here we can say WAV format category, WAV format PCM. PCM is pulse code modulation. It's how we're going to take the audio format and put it into bytes. We don't know yet exactly what that encoding looks like. We'll find out later. The reason we want packed here is so that, because people asked in chat, the reason we want packed here, or the reason we want C here is because in the Rust representation, the compilers are allowed to reorder the fields. And we know the fields have to appear in exactly this order. The reason, and repr C will do that. The reason we want packed is because we know these fields have to appear in this order with no padding in between them. Whereas with C, the compilers are allowed to inject padding between the fields to make them better aligned to CPU architecture and the like. And we don't want that. We need them to be exactly in this order with no gaps. Hence the packed. Okay, what comes next? Channels, 1 for mono. Let's do 1 channel for now. Samples per second at which each channel should be played. So here we're going to do 44,100. And average bytes per second. The average number of bytes per second at which the waveform data should be transferred. Playback software can estimate the buffer size using this value. I guess this is... What did we say? So we said 16 bits per sample. So that means 2 bytes per sample times 44,100, right? That's how much we would expect to get. Times 1 channel, but there's only 1 channel. Block align. The block alignment in bytes of the waveform data. You need to process multiple of block align bytes of data at a time, so the value of block align can be used for buffer alignment. Oh, do you need the wave format prefix for enum members? No, I do not. PCM. Much better. I don't know what to put for block alignment here. Playback software needs to process a multiple of block aligned bytes of data at a time. 64. Sure. The next thing it rightfully complains is we're trying to write out a thing that's a struct and it wants to write out bytes. And here, there are a couple of ways we can do this. The easiest one is probably just to, like, we want to take this and we want to cast it to just bytes. There are, so there's been some work on safe transmute that would make this a lot nicer to work with, rather than the thing we're actually going to do, which is to say we're going to take a reference to this. We're going to cast that to a const format chunk common. Then we're going to cast that to a const u8. And then we're going to cast that to a... Actually, we're going to do that slightly differently. We're going to say format chunk is... Actually, we're gonna do it even more annoyingly. We're going to make a little helper. We're going to say write as bytes. It's going to take a reference to a t. This does probably need to be unsafe because it can end up reading padding bytes. And it's going to take a out, which is going to be an impl write. Return result stood IO error. And here's what it's going to do inside. It's going to say as bytes is t. Why am I getting await? Why is await an option? I don't want that. I want t as star const u8. Actually, I want pointer, and then I want to return std slice from raw parts. That's going to be a pointer and std mem size of t. We can actually just call this cast to bytes instead, not take the out, and then it just returns you a U8 slice. Right. First need to cancel it as a const t and then const U8. And this is going to be unsafe. And this is no longer a result. I'll explain this in a second. And then now I should be able to do cast 2 bytes of this guy. Ooh, gotta get my parens in a row. There we go. Okay, so what does this do? So here's what this does. Cast to bytes takes a reference to a t, and it gives you back a slice of the bytes of that type. So what we're going to do is we're going to take the reference to a t, we're going to cast it to be a raw pointer to a t, and then we will cast that to be a raw pointer to a u8. And so this is now a pointer to the exact same place, but the pointer is of type byte instead of type t. Then we're going to create a slice. So in this case, it creates a u8 slice because the pointer we pass it is a u8 pointer. And then we pass it the size of t as that is the number of bytes that we know this points to as valid data. And then we unsafely return this as a slice. Now, the reason this has to be unsafe, the reason there isn't a safe version of this, is imagine if t contained padding bytes. If t contains padding bytes, then this would allow you to end up reading those padding bytes. But those padding bytes might be uninitialized memory, like the compiler didn't put anything particularly in there, and reading uninitialized memory is no, bad stuff. You're not allowed to do that. Whereas this would allow you to do it, and therefore it has to be unsafe. And so if we put a safety comment here, only safe to call on packed types. I think that's the only restriction, actually. Anything else you pass here is fine. And then the requirement from raw parts is behavior is undefined if any of the following conditions are violated. Data must be non-null. It is non-null, right? Because we got a reference to t in, so we know it points to something. Valid for reads for len times size of many bytes. That we know because we know that the thing is size of t long. So len here is where we pass in size of t, and size of t is size of u8. So that's fine. It must be properly aligned, which doesn't matter for us because bytes are always aligned. The entire memory range of this slice must be contained within a single allocation. That's also true, right? We know that there's t. There was one allocation of a t, and this is a pointer to that whole allocation. Data must point to len consecutive properly initialized value of type t. This is the thing that puts the restriction on the input t must not contain padding bytes. And then mutations and stuff, which we don't care about. So here, what we can do is we can say safety. Pointer is valid for until pointer plus size of t, since it was a reference to t, which is valid for size of t. And pointer to pointer plus size of is valid since we had a ref t, and pointer to pointer contains initialized bytes by the safety requirement of this function. A bunch of questions. Let's see. Why not just serialize it instead of casting pointers? So if you derive serialize for this, the question would be, what are you going to serialize it as? So there are formats, I think, that will just like write out the raw bit value of a given underlying field. But actually, this is a good thing you called me out on here. This will directly write out, like we're casting it to bytes, right? So whatever endianness this value is in is the thing that will go on the wire, go in the file. And almost certainly what we're going to end up with is that this will be big endian, and I'm assuming these numbers are all little endian. Actually, let's find out. So like whether the higher value or lower value goes first. Let's go ahead. Wikipedia endianness. So for those who haven't been exposed to endianness before, endianness is basically when you have let's say a 32-bit integer, so like a 4-byte integer, is the first byte, so the one that comes earliest, is that the one that holds the higher value bytes or the lower value bytes? So little endian is the lower value bytes come first. Big endian is the higher value bytes come first. Right, so here you can see this is the higher value byte. It's the one that's 2 to the power of, however long you go to get to the 4th byte. I can't count right now. Those go first in memory, whereas in little endian, the trailing end, like the ones that have that are hex wise, one base 1 go first. Then the ones that are base 1 byte more, so the 256 go here, and so on. And you'll see here that where's the... Yeah. So a big endian system stores the most significant byte at the smallest memory address, least significant bytes at the largest, and little endian system is the opposite. Both of them are widespread, and this is part of the problem, is that if you just write it out in whatever you're in, the chances that you will match whatever the spec you're trying to match is like 50-50. Not to mention, if we run it on my computer versus someone else's computer, they might get different results. Now, in practice, you'll find that big endian is usually used in network protocols, and little endian is usually used for processors. So my CPU is little endian. Most networks are big endian, but again, not guaranteed in either case. And so if we go back to RIF and we look at their representation of numbers, which was, I think, pretty early on. Actually, let's just search for endian. Really? No mention of endian, huh? Endian. Data is stored in little endian byte order. Okay, thanks, Wikipedia. Okay, so these have to be little endian, which happens to be what my computer is. Now, we have an option here. We can either just leave it at U32 because both of them are little endian, everything is fine. Or what we can do is we can use a type that will encode the endianness directly in the number. So for example, if you look at, is it the encoding crate? No, that's not what I'm after. Is it byte order? Byte order. Yeah. So if you look at the byte order crate, the byte order crate gives you types like big endian and little endian. And I think they also have... this is just a mechanism for serialization. What I really want is a an actual type I can use would have been nice. Byte order. Sort by recent downloads. The zero copy crate. Actually, maybe we should just use the zero copy crate. The zero copy crate lets you basically do the stuff we're now doing, but without unsafe. Because it's essentially a precursor to things like safe transmute. And so here, if we scroll down, you'll see it gives you, where are the modules, byte order. It gives you types like U32, for instance, but it's generic over the byte order. And so you can have a type like U32 parameterized by big endian or little endian, so that when they are cast, they end up with the right endianness. Do we want to go down the whole rabbit hole of zero copy right now? Yeah, right. It makes me a little sad. But the alternative is that we can't do this cast, right? So the alternative would be that we write out the fields one by one, and we do it manually by specifying the byte order. But I'd much rather be able to do the cast here. Yeah, all right. Let's do it the other way. Focus here should be on audio. It should not be on zero copy. But I am a little tempted because I have a suspicion we're going to have to write out a bunch of different ones of these. And writing out all the fields is pretty annoying. Let's do it. It's an interesting thing to explore. So let's do, no, that's not where we want. We want streams and what we call it, truff. So we're going to do cargo add zero copy. I believe zero copy is actually pretty straightforward. So if we do, I really wish they had a get started quickly one. I think they do on their repo. So if we go here and we go to, really, there's not an examples? I feel like I've seen an examples. Well, what we want is into bytes. Ah, there we go. This is indeed what I want. So I would like here, please, derive of into bytes. And then we'll use zero copy into bytes. Ooh, what's into slice? That's looks even nicer. But see, it gives us helpers like write to IO, which is exactly what we want. And then I will go down here and I will change these. So this will no longer be... What? Am I confused? Aha. Oh, I need to, that's because my cargo toml down here needs to say version is this, features is derive. Find out I can't type. Yeah, so now it's going to tell me that they're not satisfied. And the reason they're not satisfied is because we're using the raw integer types, which don't specify their endianness. And so here, this is going to have to turn into U16 and oops, U16. And we said it has to be a little endian U16. So this is going to be the same. This is going to be a little endian U32. And this is going to be a little endian U32. And then here, we need to also derive into bytes for our thing down here. And this, interesting. How does that even work for a U16? I wonder. So into bytes, what happens if I derive this on an enum? Because I use this U16 here is still ambiguous what endianness it is. So how can I simply derive it? It works for U8. Let's go here and see error messages, analysis. If there's an enum, it must have a defined representation. Does that. Must have no padding bytes. Its fields must be into bytes. Interesting, but how do I specify the endingness for this? This feels like something's missing. Let's go see. Let's go see what other people say. Enum, repr, endianness. Endian. Aha. Okay, what actually changed? To ensure consistent endingness for enums with multi-byte representations, explicitly specify and convert each discriminant using LE. But the macro doesn't enforce this. Interesting. U32. Sorry, U16. All right, well, we did that. And now this becomes a lot easier. So if we now go back here, that's in theory all we need to do. And if I now go back here, you'll see that I now have an implementation of the trait into bytes. And so now, instead of my cast to bytes thing, we should be able to do this and then say you write to IO and give it out. Oh, where self is immutable. So that would be if I do this maybe, then I can write to IO. So we got to turn all of these into their appropriate representation, which should be a no op because we're turning little endian, which is my CPU, into little endian, what we specified here. It really doesn't like this for some reason. Why don't I get write to IO? Where self is immutable. Okay, what implements immutable? Aha, yes, there is no interior mutability in either of these. So we can say immutable. And then we can do the same for this. And under the hood, what this implements is the same thing as safe transmute, which is really just all the same transmute things we had, but they're checked at compile time. And so it basically checks that you have no padding bytes, checks that you have endianness specified for all fields. And as a result, it allows you to cast into bytes safely. And now it should be happy with me. Still not happy with me. Why is it not happy with me? Well, okay, so one trick here, if it doesn't understand that this type exists, you can force it to be slightly more helpful by saying into bytes : : so fully specify this, and then do this. Am I... What version do I have? 0848. 0848. Are there feature flags I need to turn on? What? What? where self is immutable and W is right. Those are both true. Are there multiple into bytes? Like if I go to definition here, has mute bytes, yes. Right to prefix, right to suffix, right to IO, if config feature stood. Do I need to enable stood? Oh, the stood feature is not on by default. Wonder why. That's an odd choice, but okay. Right to IO. That's fine. So now we get to do this, and we can get rid of our unsafe function, which was just a helper anyway. Cool. So let's now erase all of that stuff we looked up and go back to our spec. Okay, wave 56, right? Great, so we've specified those. We don't know what block align does yet, but that's fine. The format specific fields, because this is 0 more bytes of parameters. Which parameters occur depend on the wave format category. Well, we specified the format category 1. And oh, these are proprietary wave format categories. I wonder how far those went. Okay, so that suggests that there's no format specific fields. So what else do we have? Then it's fact chunk, queue points, playlist, and associated data list. So all of these we can just omit. These chunks we don't need because we don't have that information. So now we want to go to the wave data. So now we get to PCM. So now we've written out. Actually, we could have even more of an helper here actually, which is something like write chunk, right? So write chunk is going to take a 4cc, which is going to be a U84 reference to, sure. It's going to take a reference to T. This is going to be generic over T is into bytes plus immutable. It's going to take a W, which is a write. And it's going to take the IO. The mute out is going to implement W, and it's going to return a result of nothing and stood IO right. Error, I mean. And so now what we can do is have this write out these plus this out. No, I mean T. So this will now write out the 4cc and then the size of T in the right format, which is the size of the chunk, and then write out the actual chunk. And now we can replace all of this bit with write chunk of B format space and this thing and out. And this can be a reference. Doesn't even need to be a reference really. If they've implemented this trait well, they have. So we can give an owned one here. What this means actually, so here I'm now giving not a reference to this T, but just a T directly. What this means is that the into bytes trait must have an implementation, like in the 0 bytes crate, there must be a implement into bytes for reference T where T implement into bytes. This implementation has to exist inside of 0 copy, because otherwise it would not have worked to do this. right? Format chunk common, that one implements, we know this type implements 2 bytes. That we know, right? Because we derived it for it. But this does not necessarily implement the same trait. So this must mean that this implementation actually exists in zero copy, which is why this was allowed. But that's neither here nor there. Cool. So now we have a little helper for write chunk, which might be completely useless because I suspect we're not actually writing any more chunks now that I looked at what came here, but let's find out. Oh, block align. Someone found a formula. Aha. Okay, let's chill out. Do it from the beginning. If the W format tag field of format checks is wave format PCM, yes it is, then the waveform data consists of samples represented in pulse code modulation format. For PCM format waveform data, the format specific fields is defined as followed. So we also need bits per sample. Interesting. So that means we also need to write out here a out.writeAll bits per sample, format specific for PCM, bits per sample. Actually, let's just do it. Let's write it like they are, which is word W bits per sample. And so this is going to be so word here means that it's a U16. So we're going to have a bits per sample. How many did we say? We said 16 bits per sample. So 16 U16 dot 2 LE bytes. And borrow that. Oh, and this needs to just be given mute out. So that's what it asked for. The bits per sample field specifies the number of bits of data used to represent each sample of each channel. If there are multiple channels, the sample size is the same for each channel. For PCM data, the average bytes per second field of the format chunk should be equal to the following formula rounded up to the next whole number. The number of channels, right? I think this we already have, right? The number of channels, which is 1, times the number of bits per second, which is this, which is what? Yeah, okay, bits per sample divided by 8, so that's 2, and this. But why does this say bits per second? Oh, and the divide by 8 ends up being to both. Okay, great. I think there's no bits per second, right? There's samples per second. I think this is just wrong. This should say samples per second. Because you can't, bits per second times bits per sample makes no sense. Pretty sure that's wrong. Pretty sure common and specific fields are part of the same chunks. You likely need to include the size of bits per sample in the chunk. You're probably right. Okay. We will do that with format specific fields. Needs to implement. Format specific is going to be FSF. And then we're going to have this whole thing again. Wave format chunk fields, or format chunk, actually it's PCM, I guess, which only has, what was the name of the field? Bits per sample, which is going to be a U16. And then we're going to do here, format specific is going to be format chunk PCM of 16. Bits per sample, 16. Yeah, Clippy, thank you. Right, so we make this generic and then we make this at the end, and this is the only generic instantiation we actually use. The reason we need this is because, as someone pointed out in chat, the chunk, the format chunk, has a length, and that length needs to include this field. So if we just write the field after, it will not be considered part of the chunk, and everything will be out of whack. Okay. Fine, Clippy. Stop yelling at me. The block align field should be equal to the following formula rounded to the next whole. The number of channels times bits per sample divided by 2. So 2. Right? So this is supposed to be channels times bits per sample divided by 8. Bits per sample is 16, divided by 8 is 2, times 1 is 2. So 64 would have been wrong, but I don't think it would have mattered because it seemed to be about buffering in the clients, and if they buffer 64 bytes, it's not the end of the world. In a single channel wave files, samples are stored consecutively. For stereo wave files, channel 0 represents the left channel, channel 1 represents the right channel. The speaker position mapping for more than 2 channels is currently undefined. Good old 1991. In multiple channel wave files, samples are interleaved. The following diagram shows the data packing for 8-bit mono and stereo. Channel 0, channel 0, channel 0, channel 0, channel 1, channel 0, channel 1. Okay, so we're just writing out the samples in order. We're using 16-bit, and it's little endian. Low order byte, then high order byte, low order byte, then high order byte. Cool. Each sample is contained in an integer, I. The size of I... Is this whole thing a chunk? No, this is just the data. It's the data. It's the trailing data of this wave chunk. This is not a wave chunk of this riff chunk. Oh yeah, this is also wrong, right? This should be channel 1. Cool. Each sample is contained in an integer I. The size of I is the smallest number of bytes required to contain the specific sample size. Size of I. Yeah, this is just the bits per sample. The least significant byte is stored first. The bits that represent the sample amplitude are stored in the most significant bits of I, and the remaining bits are set to 0. For example, if the sample size is 12 bits, then each sample is stored in a 2-byte integer. The least significant 4 bits of the first least significant byte is set to 0. Okay, so this just means that even if you have a format where you only record, let's say, 12 bits, you still have to store 16 bits, and you just pad with zeros. Because we have a sampling size of 16 bits, we don't need to do that. Okay, I don't need them to tell me how many ints you can store in bytes. That's fine. I'm glad they tell me the midpoint value. Thank you. Example of a PCM wave file. Riff, chunk start, wave, format chunk start, fields, data. So data is a chunk. Interesting. Okay, so that means we have to be... And this is a chunk that we also don't know the size of ahead of time, right? Although arguably we could, because if we know how much noise we're generating, then we actually know the size of the file ahead of time. So it depends on whether we want this to be like the user hits Control-C and then we stop generating noise, or whether we just always want to generate a fixed amount of seconds, because then we can actually know. So how about we do that instead? So we say let seconds is 10. Fine. Duration in seconds. Don't want to support partial seconds, because now we can actually compute, right? So we know the number of bytes per second, so we can actually compute these. We know that the that samples per second is 44,100. This is a U16. U32 samples per second. U32. We know that the number of channels is 1. That was a U16. We know that average bytes per second as a U32 is channels times samples per second times bits per sample. And we also know that bits per sample is 16 divided by 8 as U32. As U32. So now this is samples per second. This is average bytes per second. This, I guess we can make be channels times bits per sample divided by 8. So we can actually follow the formula. And this is going to be bits per sample. Because now we can compute length in sample data length is going to be average bytes per second times duration in seconds. So we know exactly how long the sample data is going to be. And then we can actually compute this one as well, because we know that this is now, if we pull this guy out, format is going to be this. Right. Oops, format. And so we know now that this here is going to be sample data len. And this is going to be sample data len plus 3 times 4, right? So 3 4cc's, wave, format, and data, plus the size of format. And here we can use size of val and give in format. And this as U32. So now we don't need to go back to edit the file. We still could if we wanted to, but let's keep it simple from now. You probably want to measure it in samples rather than seconds. Oh, you're probably right. This is going to be samples per second times duration in seconds times channels. I mean, it's the same as average bytes per second, right? So we're just redoing the, I'm going to keep it this way because we happen to know that this is like we would just use the same formula. We know it's not average. It's a fixed rate encoding. Okay. Great. And then it's just the wave data. Storage of the wave data. The wave data contains the waveform data. It is defined as follows. Wave data is a data chunk or a data list. A data chunk is... This is definitely wrong. This spec for the format, because this already says data is a chunk that holds wave data. But wave data is... or can be a data chunk, and data chunk can be a data chunk that holds wave data. So you would just end up with data all the way down. There's no wave list and silence. It can also be a data list. Okay, what is a data list? Do they mean a wave list? Okay, we're on page 60. Let's go back and see what lists are. String, escape sequences, name type, optional sequence. Okay. Okay. But what is a list? Is there data list here? No. Storing strings. List chunk. A list chunk contains a list or ordered sequence of subchunks. The list type is a 4-character code that identifies the contents of the list. If an application recognizes the list type, it should know how to interpret the sequence of subchunks. Okay, so list is a chunk where the first part of the chunk is the type of the list, followed by a list of chunks. Okay, but then where does the actual... Okay, is there a list data? Info list chunk, CSET chunk, junk chunk, junk chunk. That's fun to say. CTalk. I want... Okay, and then it just stops. Okay. Data. Okay, wave data. But what is a data list? Data list. Appears only once in this document. Cool. So data list is probably wave list. I love this spec. We could go to Wikipedia and check, but it's more fun to read the spec. So this means wave data can either be a data chunk or a list. If it's a list, then it's a list of data chunks or silence chunks. I see, because this is not a list. Okay, but where does the actual data go? I understand this one. Where's the actual data? Data chunk. Yeah, so don't use zeros, use silence, that's fine. But okay, so that's all we get. That's all we get. All right. The wave data contains the waveform data. It is defined as follows. Because this is still a chunk, and that chunk is defined like this. And that leads with data, but that contains wave data, which is this. So where do the bytes go? I feel like it must go here, right? Like it's got a data chunk has to just hold, but then why does... Oh, no, this is an example. I see. So I understand. I understand what's happening. It's not that you must start at data. It's that you can either start with a list if you want to inject silences, or you can directly inline the data list. So a data is a wave data. This is wrong. Like a data, this here should not say wave data, because this can't recurse. The moment you put a data chunk, those are just the bytes. I'm like moderately sure. So what that would mean is because we don't care about silence blocks. We don't need the list. Therefore, we can directly use the data chunk representation, which means we just give data, but it has to be lowercase data, and then a data chunk, and then we just write the samples. Because otherwise you would read this as this could be data, 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 and you can just keep nesting them, which makes very little sense. And also then there would be nothing referring to wave list. So I think this should be wave list. And so it's just saying if you can have a list if you want data and silence alternating, but you could also choose not to use a list and just directly embed the data, which is what we will do. Let's try and see what happens. The thing that will now be difficult is how do we generate a file that we can realistically test? I think what we should do is try to generate a file that just has a static tone in it, because that we should be pretty easy to find out whether that's reasonable or not. And so now the next question is what is actually stored, and we saw it mentioned somewhere here that it's amplitude. Amplitude. Yeah, so it's sampled amplitude. So what they're after is, split your recording into samples by time, and each sample should be the amplitude of the sound, the movement in the air, if you will, at that point in time, and then give me lots of those samples. But when I say, for example, a pure tone is a frequency. And so the question is, how do you go from a frequency, which would say frequency on the x-axis and amplitude on the y-axis, and I would say I want a 80 hertz tone, right, which is just a spike at frequency 80, and then with some amplitude, which would basically be the volume, and then turn that into this amount of time and this amount of this amplitude over this time. And for that, you need a fast Fourier transform, or a Fourier transform, really. So let's go look at Fourier transforms. Fourier transforms, Wikipedia. Okay, so a Fourier transform lets you, let me see if they have a good, there's a lot of math, but I want to see the plot. Give me a plot. Give me a plot. How do they not have just like the basic plot of frequency to amplitude? Oh, it is here. It's just, is this an animation? It is an animation. Okay. Well, that's also not what I wanted. No. Go back. So a Fourier no. Aha, close. I can't click that because it's behind my camera. So the Fourier transform takes a function, that's fine. The Fourier transform takes a time signal and turns it into a frequency signal. So x-axis is time, to x-axis is frequency. What we want is something that goes the other way. So it goes from frequency to time. And so that would be an inverse for maybe it's in the same document. We want an inverse Fourier transform, which goes the other way. So it takes frequency to time. But I just wanted to see if they had the nice like graphic for it, but I don't see it, sadly. None of these make me happy. Aha. Yes. So this is a time signal. So this is the x-axis is time, the y is amplitude. Y is always amplitude. And if you look at a signal like this, the reality is this is really the overlapping of multiple different signals based on frequency, right? So this has some frequency, this has some frequency, this has some frequency. And if you sample them at one point in time, what would you get? And you get this sort of interposing of all the waves that dictates what the amplitude is at any given point in time. And if you sample enough of these, then you get a sort of view of the overlapped underlying frequency signals. And so if you do an inverse Fourier transform, Oh, sorry, if you do a Fourier transform, it takes you from the left-hand side here, from a time-based system, to the right-hand side, to a frequency. So it says this, these sort of time-based samples you've given me, here are the frequencies and what amplitudes they're at in that signal. And the inverse Fourier transform goes from this thing, which is frequency on the x-axis, and tells you at these discrete points in time what would the amplitude be if you sampled this at that interval in time. And so what we want to do in this case is we want to just stick the amplitude all in one frequency, run an inverse Fourier transform to get the time-based signal, and then take that and just stick it in the sample data. Oh yeah, we could also use sine. Maybe we'll just do we're going to need an inverse Fourier anyway for the noise, so we might as well stick it in there right away. Okay, so what we're going to need is an inverse Fourier transform, and this is something I don't want to implement myself, especially because it would be very slow. So let's do Fourier. Sort by recent downloads. Ha ha ha, excellent. Let's look at both of these. Both seem to be maintained. Let's do our little bit of due diligence here. We don't need to do very much. This is not a project that matters. Rust FFT certainly sounds official. 17 contributors, 8. Let's look at the actual contributor graph too. Wait, the maintainer of this one is one of the top contributors to this one. I'm deeply confused. But that was in 2020. And then after that, they moved to this repository. Oh. Mighty suspicious. This certainly seems to be more maintained. Or at least have more people working on it. How are we looking activity-wise? Okay, so this seems to be more of a one-person thing, even if they were one of the main contributors to this one way back when. All right, let's go look at docs. I think, honestly, either of these would be fine, but let's then go back here and say, look at the docs of both of them and see if they're both actually... Oh, one was a wrapper for the other. Oh, is a wrapper for Rust FFT that enables fast and convenient FFT for real value data. Oh, interesting. I guess it's in the name, real FFT. But we don't actually need reals. Let's see how this works out. So create an FFT planner and call plan FFT. Choose which to use. Also exposes individual FFT algorithms. All right. And does it have, let's hope it also has inverse as well. Yeah, plan FFT forward. I'm assuming it has inverse. Yeah, okay. Plan FFT inverse. Interesting. And what implements FFT num, I wonder? From primitive. Oh, it uses num traits. I see. Wait, so this already does F32s and F64s. Why? I don't... Directly avoids the need of converting real value data to complex before performing FFT. Oh, it's because I don't need... So fast Fourier transforms lets you do... to transfer complex numbers. Like, let me rephrase. If you look at a... if you look at a waveform, you have the amplitude and you have the phase of the signal over time. And we don't need to track here. Let me think here. I don't think we need to track the phase of the audio signal. Basically, so the Fourier transform is pretty powerful. It can capture things like how many times has this wave gone through, not just its frequency, by capturing sort of complex numbers here. But we don't actually need that for audio. So I think actually maybe real FFT is nice because it gives us a simpler mechanism, because all we need are the amplitudes. It sounds like, because one is the wrapper of the other, it feels like we can probably just use real FFT and then switch if we don't like it. So let's do that. Cargo add real FFT and Rust FFT. What do you really need the Fourier transform for? I think the noise functions can easily be defined in the time domain. They probably can, but they are usually described in terms of the frequency domain. And so it feels nicer to operate there. Length here, this we're going to have to modify after a little while, but that's fine. We want a FFT planner. Okay. Let's go ahead and just copy paste this and see where we get. So, right, we want to plan an inverse. We want a make a vector for storing the spectrum. No, the in data here is going to be the spectrum, and this is going to be time. So because it's an inverse, the input is going to be in the spectrum and the frequency domain, and the output is going to be in the time domain. Is it still process? Yeah, it is process. It should go from spectrum to time. And it's going to be the output. Cool. So if we now take, so spectrum is going to be a vec, and let's just like eprint line spectrum. It's going to be spectrum.len. Don't think we need these. Time is going to be time.len. In fact, let's try to run this for the first time and see what happens. Okay, so we said we want a length of 256, and the length is the length in the time domain. And I think this applies for the forward as well. So what we're saying is we want this many samples in the time domain, and then the FFT is going to give us back, or it's going to tell us how many samples do we need to give in the frequency domain in order to get that many samples in the time domain. So in this case, you'll see in the time domain, if we want 256, we're going to end up with 129 values in the frequency domain. And so here we can now pick a arguably a random point in here. We can set that to basically the amplitude we want this to have. And this is where it'll be interesting to see. I think the amplitude here is probably in decibels. We might find out if we generate a really, really loud noise. So how about we go with minus 30 dot into dot. Okay, and then for sample in time, we're going to do out.writeAll. And I guess just to make this slightly faster, we'll also do use std.io buffwriter. And then we'll now here, when we create this file, say that mute out is buffwriter new of out. We're going to out.writeAll. So sample here is going to be an F64. We want to round to... Isn't there a nearest? I think F64 has a way to... I guess round is the nearest integer. And then we'll cast that to... we'll actually do U16 try from here. Just because I want to make sure we don't end up overflowing the U16. And then it's 2 LE bytes. As U60. Oh, that's interesting. Can the amplitude even be? It can. So what is the amplitude if we go back here to this? The amplitude, huh? They don't actually say what the amplitude is. Yeah, I understand that's the maximum value, but what's the... Okay, I mean, it's an integer, and it's an unsigned integer, so... Oh, wait, what? 16-bit PCM is signed then. Is it signed, or is it just... Yeah, it must be signed. Okay, so it's... So 16-bit PCM is signed 16-bit PCM. But if it's 8 bits, then it can't be negative. Yeah, okay, yeah, here. So 1 to 8 bits is unsigned. 9 or more bits is a signed integer. That still doesn't tell me... Okay. So that means this has to change slightly, because actually only this has to change. It's an I16. This also has to be I64. I just want to see what we get here. That's what I want to do. Out.flush is going to be the end. This is not going to be the right number of samples, but now we should have an audio.wave. And if we now do... Oh, didn't I install a thing for this? But we could do hex dump, but that's fine. Audio.wave. Okay. Actually, what am I doing? I can just print out these values as they come. So we can do amplitude is this, and then here we can say amplitude 2 LE bytes, and then we can print line amplitude. Yeah. So if you see, it goes minus 60, 0, 60, 0, minus 60. So what we end up with is a wave, right? So in the time domain, we have a signal now that goes between minus 60 and 60, and it goes in a sort of, I mean, without visualizing, without setting a reference for the actual time, it's hard to say what it actually produces, right? But this is clearly a wave because it goes up and down, and the amplitude of the wave is here, sort of the highest amplitude is 60 and the lowest is minus 60. If we changed this to, let's see, be at 80 instead, so this would be a higher frequency, we should expect this to move more rapidly. Which is hard to tell from this, but if we had a plot, we have a plotter. What did I call it? Dings? Ooh. I forget how dings works. We built this in another stream. Oh no. Dings-h? Oh no. Dev tools. No. Streams dings. Git pull. No, I don't want to do that. Why does it need my... Okay, fine. I'm trying to remember what the arguments to this was. It was like... X is row. But I don't actually remember what we set the configuration arguments to. X is row. Opt. Oh, args. X is row gets set on by dash X. Okay. Things dash no dash X. Not yet implemented. What? Clearly, we did not build things well enough to... Like, why won't it just... Because this is a completely useless plot. Oh, it's... No, actually, it's not. This is actually plotting the right thing. It's just that you don't see the line in between them. But it is a thing like that. So, in fact, here, let me try a lower value. So, let's go down to, like, 10, right? So this is a wave. Yeah, that's not particularly helpful, is it? If we did 1024 instead. Not particularly helpful, is it? There's not enough width in the... if I did fewer, it's because my terminal isn't wide enough. So if I do... dash W 128. Is it not dash W we set to be the dash D 128 by 80. It didn't like that at all. Fine, 80 wide then. I just want to plot it. Oh boy. Frame. There's a bug in our thing somewhere. Min X, max X. I thought this was like self adjusting. Clearly we have some way to go on this one. 60, 80. The len is 41, but the index is 120. We could clearly do better here. What if I just GNU plot it instead, and do -e plot 1. Oh, it's been so long since I used GNU plot for this stuff. How about you do GNU plot single column of input. Next stream should be to finish. It's true. To finish dings. It's like plot dash using 1. Using pseudo columns is what I'm after. I want :1. X range is invalid. Pretty sure there's a way to tell GNU plot. I thought it was fine to just say using 1, but it doesn't want. Oh, wait, what? We're panicking. Panic at line 71. Oh, that's because this now has way fewer columns. Oh, so maybe then dings was working just fine. Dings was working just fine. Okay, great. So dings wasn't the problem. It was, I just misread it as where the, okay, great. Cool. So this is a plot where we set, like, let's do a low frequency. So here you can see the waveform, right? So you see this is now you can actually see the waveform. And I think I can do like dots. Is that the args? Oh, dot. Well, okay. All right. Settle down. Okay, so that's this one. If I made it even lower, so if I said 1, you'll see the waveform is much longer, lower frequency. If I make this higher, and there's sort of a limit to how high I can make it before it becomes inscrutable, but you'll see this is a much sharper waveform. So again, higher frequency. So this means that it is working. The transform is working the way we would expect it to. And then now what we need to do is set the so the length of the window that we're trying to turn this into. So let's say we wanted to generate 1 second of samples, right? So we have samples per second is the thing we know we want here. That is the number of samples we want to generate per second. So this is 1 second of samples. And in that second of samples, we want, so the question now is, what is the key here? If we print out here now, spectrum.len without setting 30. Oh, as usize, please. What? Oh, yeah. Don't print the amplitude, please. So we have 22,000 frequencies, and the question is, what is the lowest frequency and what is the highest frequency? And I think the frequency here is, and this is where I need to go back to my thinking. Not to go back to my thinking. Go back to my school days. I believe these frequencies are like 1 over the sample rate spaced apart. So like, for example, so spectrum of 1 would be the waveform at 1 over 44.1 K. Isn't there's a formula for this? I think this is where I need to go back to the maybe this has it actually. Okay, that's not helpful. Hertz. Yeah, it's 1 cycle per interval, and because we've set the interval to be a second, then 1 here is the wave that has 1 cycle per interval. So a frequency of 1 hertz. This is the one that has 2 cycles per interval, so it's 2 hertz because we've set the interval length to be 1 second. And so if we wanted a tone at what's the frequency of this is something I probably should know off the top of my head, but like a pure A tone. Online tone generator. That's not actually what I wanted, but sure, 440 hertz. Why not? So we want that. We don't actually know what amplitude we want, but let's just say -30 for now. And then we'll bump it up as needed. And then we'll get, now we actually want to write these amplitudes out. And then once in cargo run. Okay, so we now have a file, but this is for 1 time segment, right? And so what we actually need is for interval in duration in seconds, we need to do this. Now, this won't be quite right because there's going to be a discontinuity potentially between the end and the start of an interval because we're just starting the tone over, but I think that's probably okay. U32 is not 0 to duration seconds. And we don't actually need interval. And this. All right, let's see. File audio wave. Okay, riff, little endian data, wave audio, Microsoft PCM 16-bit mono 44/100 hertz. Okay, that seems good. ffmpeg-i says there's a 10-second audio in there. That's what we tried to generate. Bitrate we don't care about. PCM signed 16 little endian. Yes, that's what we have, which is what the format we specified was. So maybe this works. Let's just see what happens. Audio to wave. I hear a tone. It's very low. It's very, very, very low, but it is there. Let's go. No, that's too much. And I think this is in decibels. Yeah, okay, let's generate again. Here, let's try again. This should be quite a lot louder. Not quite a lot louder. Let's... There's definitely a tone here. I swear I hear it. But I feel like now I hear it less, which is confusing. What? Yes, I hear it now, but if I made it If I make it louder, it gets quieter. Like, can you hear it? It's not just me. Let me see if I do like 120. There's clearly a tone. Okay, let's go more. Right? But why is more negative louder? Isn't the input of an inverse FFT amplitude and not decibels? Yes, I think that's true, but that still doesn't explain why more negative amplitude. Oh, this is probably linear scale. It's not decibel scale. That could very well be. That's a pretty clear one. But I'm still not sure why it's negative. Right? Because, oh, maybe it's the same volume when it's positive. Okay, good. So it's actually just because if you flip the amplitude between -1000 and 1000, it's the same wave, it's just out of phase. Like when it starts, like when it's at its maximum compared to when it's at its minimum, shifts. But we don't actually care about the phase of the signal here, because whether the sine wave goes back and forth like 440 times a second. And so whether the peak of the amplitude is at, millisecond 0 or millisecond whatever, like a few milliseconds later, we can't hear the difference. It's still the same tone. This is what I mean by phase. And that's the thing that the Rust FFT would give us, is it would allow us to capture the complex signal, which means also setting the phase. Real FFT just doesn't let you set the phase, which makes the interface nicer. And we don't care about the phase. And so but we can change the phase by switching the amplitude, but we can't switch it any further. Okay, so what this means is this is amplitude, it's linear amplitude. So if we now make this 2, it should be twice as loud. Well, it is louder. I can't tell you if it's twice as loud, but it is definitely louder. Okay, so we now have an A tone. Great. So now we have a way to go from there's no discontinuity, at least I didn't hear one between the seconds, and that's probably because we say one cycle per, like the number of fluctuations per cycle is going to be, like you'll be off by so little that I guess you won't really hear the difference. But let's try to make it like a much lower one, like 67. Yeah, so it's a much lower bassier tone. And if we do like 4 times 440. Ooh, modem sound. That really reminded me of a modem. That's funny. So we don't need the complex and we don't need the 0. Oh yeah, it's not actually, it's linear in amplitude, but as someone pointed out in chat too, because of our perception of sound, which also varies by frequency, the amplitude doubling does not mean it's twice as loud, because our hearing is basically logarithmic. That's why we use the decibel scale for actual volume. So in order to make it twice as loud, you need to, someone saying 10x the sound, like this would be the decibel scale. I don't know if it's quite that bad, but it's something like it. Okay, but what we now have is a mechanism to go from frequency assignments to time assignments. So now we get to the definitions of noise. So if we go to colors of noise and we look at white noise is a signal named by analogy to white light with a flat frequency spectrum when plotted as a linear function of frequency, so in hertz. In other words, the signal is equal power, so amplitude, in any band of a given bandwidth, when the bandwidth is measured in hertz. For example, with a white noise audio signal, the range of frequencies between 40 and 60 hertz contains the same amount of sound power as the range between 400 and 420 hertz, since both intervals are 20 hertz wide. And so what that looks like is across the frequency spectrum, the amplitude is the same across all the frequencies. Well, we have a way to do that now, right? So we can say what we're going to do here is amplitude in mute spectrum. We're going to set amplitude is, and let's do something not terribly crazy. Let's do, because let's do something like, let's start easy. 256 dot into. So we're now going to generate every frequency at the same amplitude and then overlap them in the time domain and see what we get. So, oh, it didn't like that. So this is interesting, actually. So this is the U16 conversion is now failing because it's telling us you're trying to give me an amplitude that is outside of the U16 range. And why is it doing that? So let's do let OK amplitude equals this, else. Still gonna panic, panic and say output amplitude too loud. Sample. Okay, so that looks pretty loud. And the reason this happens is because when you have these like many frequencies, then whenever two frequencies have a peak at the same time, they amplify each other. And if you have more peaks and they stack on top of each other, it makes the signal louder. And so what we need is to make sure that the amplitudes, even when the harmonics, like the repetitions of the waves, even if the peaks line up between different frequencies, they still don't sort of blow the speaker. And there are mechanisms you can use here, but we're gonna try to just lower the amplitude of every frequency such that even if they add together, they don't add that much actual value. Still too loud. 10. Still too loud. 1. 0.5. Cool. I worry this might still be very loud. Just to let's. Okay, that wasn't so loud. Worried about like. That's not. That doesn't sound right. Yeah, there's a clicking. But why is there a clicking? I think what you get is you now only hear the harmonics because all the others are too quiet. So what if, okay, hear me out here. I just worry this will be very loud. But maybe not. I think so. There is something we could do here, right? Which is, oh yeah, okay. We could also open the file in Audacity. Let's try that too. But let's do unwrap or else i64 max. So that's the other thing we can do. But let's first. Audacity. See what happens. Okay. And let's open. Oh, there's too much stuff in here, isn't there? Now you get to look at all the files I have. Very exciting. Streams and truff and audio wave. Audacity detected this file to be 120 beats per minute. Would you not like to enable music view? Sure. Okay, yeah. So you see every second there's a peak. How far can I zoom in here? Interesting. I think what happens here is all of the signals start at the same time, right? Because we've set, or do they start at 0? Yeah. So I think that's exactly what's happening. So I think we in fact do need to cap it like this. I16 max. I'll unwrap or. So it was not loud? Okay, we still get the same harmonic. This is still not right. Why are we... Oh, I wonder if spectrum 0 needs to be 0. No. If you don't randomize faces, you're generating an impulse function. Oh. Yeah, exactly, because they all start with the same phase. So at second 0, they all have maximum amplitude. But I feel like there should still, if we cap that one, the rest of the signal... Why does the rest of the signal cancel out? Okay, so I think we have audio specialists in the chat who say they're canceling each other. And I'm sure there's a reason why that my math brain is not up to understanding because I haven't learned this stuff. But this does mean we need to randomize the face, which in turn means, we need to use the actual FFT thing and not the real FFT thing, because we need to adjust the phase, which we can only do if we have access to the complex settings, which let us change the phase separately from the amplitude. So we will do that. So if we go back to Cargo Toml, we remove real FFT, and we use Rust FFT planner. And then we say this is going to be an FFT planner new. And then we also need to bring in complex numbers from here. Okay. Right, and now this, I guess, has to be complex F64. Okay. So I can just make it be new. All right. Oh, I see. This make input vec we don't get to do anymore. So that means we have to... Oh, I see. So with real FFT, it would like tell us what size the input vec and the output vec should be. This one will not. All right. So how about we go back to what we had. And then we print out spectrum.len. And we print out time.len. And then we get rid of these. And then we make this be Rust FFT. Num complex. We go back to making this be the FFT planner. And now when we use their FFT planner, we have to create the buffer. And this one needs to be then this. Planner returns trait object as a FFT trait. It also exposes individual algorithms. We don't need that. FFT planner. I think that's because harmonics of a wave are aligned, and every wave has almost infinite harmonics for what we're concerned, because we're setting basically all the frequencies. I suppose, but it feels like there must be something more. Isn't it like a sequence of number? Except for prime number and frequencies, they all divide and cancel each other. Maybe. I don't know. Okay. Constructor, they have to detect available CPU features. Computes invert FFTs of size len. But what's interesting is it seems like I can create inputs of any length, but the real FFT thing specifically suggested an input vec. How does it know the input vector produce? So if I say plan FFT inverse, make input vec. I want to see complex to real. Source. Well, our FFT is even. So it gives us an even. So what is the implementation of even? For even, so there are a bunch of optimizations. It looks like it actually does. Make scratch vec. Complex 0 self complex len. So yeah, the input vec, where does complex len come from? Complex len. Oh, divided by 2 plus 1. I see. So this is samples per second divided by 2 plus 1. Right. So this is the Nyquist-Shannon, right? Like these are the frequencies we can capture with this number, this sample rate. Expected U size, find a U32. Right, as U size. So we're setting this all to be zeros. Doesn't actually need to be a vector. Can it just be this? And then this is going to be spectrum. And then the output vec time is just going to be a vec of 0 of length samples per second, and then we process. Right, so if we go back out now to here, oh, it processes the buffer. It processes it in line? What does process do? Oh, output order. FFT planner. Plan inverse. I see. Yeah, okay. Convenience method allocates a vec with the required scratch space and then calls process with scratch. So if we call process, it is in place, but it internally allocates a vector. If you want to reuse the same allocation across multiple computation, consider process with scratch instead. Okay, so let's then do scratch is going to be vec oh, interesting. No, in place is fine. Yeah, so it will actually tell us with capacity is going to be R2. Actually, this is also wrong, right? This is be C2R because it goes from the complex frequency domain to the real space of time amplitude. And we want to use C2R dot get notes. What's the helper called? Get in place scratched len. Get in place scratched len. And then we can say process with scratch of buffer and scratch. But I actually want it to not be in place because I want to keep the spectrum for the next iteration. Now, technically, this doesn't matter because we're generating the same samples in every cycle. Right now, at least we are, right? So we could just generate 1 second of sound and just repeat that second over and over. But if we do that, the noise will sound the same every second. And I actually want to randomize the noise as we go. And so the way we would have to do that is to change the spectrum for every call. And the way we'd want to do that is to change not the amplitude, but change the phase of every complex sample. But that means I want to keep spectrum, so I don't want to do this in place. So I actually want this to be out of place with scratch, which means time is going to be with capacity, C2R dot get. This should be out of place scratch length. This should be 0 of length samples per second. SU size. And then this takes input, output, and scratch. So mute time and scratch. Right? Oh, why is the output complex as well? Okay, that's fine. It can be this. Like so. Expected this, expected. This one. So scratch. It expects all of them to be slices. So that means we can actually do mute time. So now this and this go like that. And scratch is going to have to be scratch dot set resize technically. This with zeros. Or is Scratch also complex? Probably. Yeah, okay. This feels like we can actually change. We can create a const complex 0 is actually, there's probably a trait for that. So I suspect we can do 0. Yeah, great. And here, complex 0. And then for all of these, we turn them into a slice. And now there's no result. Time is already an array. This is now a complex, right? So now the question becomes, in the complex things we send in, we need to set the phase. And so we need to set the amplitude and the phase. Yeah, and when you have the complex number, you have the ability to set the phase and the amplitude. And a complex number, as we all know, is a value, that has two components. It has the real part and the imaginary part. And the amplitude is, if you imagine that you draw a line in this space, in this XY space, the amplitude is the length of the line, and the phase is the angle of the line compared to the positive x-axis. I don't know if this is flipped for you, but whichever way it is. And so, the real FFT thing hid this from us, so we didn't have to think about it. But we do have to think about it now. And one of the ways you could do this is, right, you just set the line to be a real component of 0 and an imaginary component of the amplitude you want, or a real component of the amplitude you want as an imaginary part of 0. And if you do, you will end up with the correct amplitudes, but the phases will all be 0. What we need to do is we need to actually randomize the angles, the phases, but keep the same magnitude of the vector, if you will. In that space, which means that it can no longer be like this. Instead, it needs to be, and there are faster ways to compute this too, but for each thing here, so for each interval, we're going to have to do this again. Although we could do it now just to... No, we're going to do this properly. So we're going to do cargo new, cargo add rand. Then we're going to say let mute rand is rand RNG. And inside of here, I don't know if it matters what you have in 0th position here. Well, let's find out. So we're going to say we know the amplitude we want is, let's say, 1,000. And then we want for frequency in the spectrum. What we want to do is we want to set the real and imaginary parts of the value for that frequency. And we want to set them in such a way that the angle is random, but the magnitude is the amplitude. There's num complex from polar. Perfect. Okay, so complex, so we can do frequency is complex from polar. So polar is a different way to specify coordinates. So if you have a value in a Cartesian coordinate system, so XYZ, for example, you can specify the coordinates of a point or a vector by giving the X and Y coordinates, or you can give polar coordinates, which is angle and length. And that is, in fact, exactly what we want here, is we want to give polar coordinates, which has R and theta, where R here is the radius, so the length of the line, which is what we want to be our amplitude. And the angle of the thing, which is what we want to be random. So here we can do rand dot random. And this will generate as a completely random number of the type that we need. And in fact, it's totally fine to give, let's say, a polar angle of, I don't know, 4,000, even though I'm assuming this is probably in radians, although it isn't typed. then it would just be, you know, lots and lots of rotations. But ultimately the trigonometric function, so this ends up using a sine and a cosine to compute the x and y coordinates. We like those function, they function even if you have angles that are super high, they still compute correctly based on like 0 to 360, or rather their output values repeat as the angles rotate. And so we're totally fine giving a completely random number here, although we do need to tell it that it should be an F64. We may also, the only problem with F64 is I forget whether it can generate nans and stuff. Oh, someone put it out in chat at the same time too. I don't think so. I don't think random generates nans. I'm like fairly certain. Let's see. So if I say RNGX random, where standard uniform. Here we go. Floating point types are uniformly distributed in the half open range 0 to 1. Well, that's actually better for us. That's good we checked, because this means we can just do times standard F64 consts tau. But let's double check that this is actually radians. Cos function in radians. Okay, great. Okay. Don't you need to process FFT after setting spectrum to get the proper samples? Yes, I do. So the other thing that needs to change is we now need to recompute these inside the loop. So previously we'd compute it once and then we just take the output and print it many times. Now that we want randomness, we actually need to randomize for every iteration. And so this now goes in here, but the scratch stays can stay out here. So this goes here. We now have this. We compute these and this and the scratch. Rand. Generate a random phase, but a set amplitude. Let's make this amplitude much smaller. And now I actually think we might not get the same harmonics. So we might not need the clamping. Although it is kind of random. Now, the other thing that we're going to get out now is in the time domain, we also now get a complex number out. Now, I wonder whether, so in the time domain, what is the, do we care about the phase of the output? I don't think so. So I think we can just do, this is a complex, yeah. So I want the, is there a way for it to give me the, yeah, same as norm, right? And I assume abs and norm return the same thing. Okay, it doesn't show me what abs is. Yeah. Cannot mutate immutable variable. That's true. Okay. Let's see what happens if we try to now run this. You do not need to make it negative if phase is between 0.5 and 1. If phase is between 0.5 and 1. Oh, you can just take the real parts? Really? No, norm should give you the magnitude of the vector, right? Am I being stupid here? Like I want the... Let's see. Num traits, complex. What? Where do they get complex from? Here. Oh, num complex. I see. Show me what you got. No, I don't want scale. Yeah, isn't the norm just the... I thought the norm of complex number is the magnitude, right? From a real complex vector space to be to the non-negative real numbers to behave in certain ways, like the distance from the origin. Yeah, okay. So it is norm. Great. Cool. So let's run it and see what happens. And now we don't need complex float either. Provided FFT input buffer and output buffer must have the same length. Why? Interesting. Ah, I see. So let's fix two things. Let's fix two things in order here. First thing, this apparently needs to be the same length, but why did the real FFT thing did not require them to be the same length? Oh, probably because it was operating with reals, not complex numbers. It's either that or, yeah, okay. So this needs to be the same length now. Okay. The complex output will either be the rectangular form using sine and cosine as the basis, or the polar coordinate where you only want the real part. For real signals, negative and positive frequency components are related, so you only need positive frequencies. I see. Okay, but now because we are giving the full complexer, including the phase, we actually need the full length. That's fine. But now the other thing that's interesting here is the output here. This is always a positive number. In fact, yeah, but that means we're not making use of the negative numbers in I16s. And so what we can do to make the full use of I16s is we take it as an I64 and then we subtract it by the I16 min, or we add the I16 min realistically, right? Because the min is a negative number as I64. And so that way we get more range. Oh, that's a really loud amplitude. Okay. Oh, wait, no, it's not actually that loud. It's just a complex number. You start with a real signal in the time domain. So just take the real part. Yeah, we're not starting with a real signal. We're going from the frequency domain, which is complex. Let's see what this sounds like. But the thing that we're still going to run into is we still now have the possibility to peak the spectrum, like peak over I16, which means this still needs to be this. See what happens. That was pretty loud, but that kind of sounded like white noise. 32. Still pretty loud. 8, 4. Yep, that's noise. That sounds like white noise, right? Like the volume here is hard to control. Okay. And then if we go to Wikipedia, white noise. I mean, it's different volume, but those sound very close to each other. But yeah, there is a pulse. But why is there a pulse when we're randomizing the phases? But why is there an Oh, is the impulse because of spectrum 0? No. You have a massive DC offset click at the start of N because of taking the norm and adding I16 min. Why does that make a difference? I guess part of the problem here is I don't actually know what the complex parts. Instead, what happens? Whoo! That was way louder. Still very loud. Uh, 0.5. Still very loud. Why? Just take the real part once. Oh, just I see what you mean. I understand. What we want to do is take the real can also be negative. So we don't want to subtract I16 min to a number that's already negative because that would make it way louder. So we want to take this. Okay. All right. So we want to take this as I16. Then we want to clamp it to I16 min value and I16 max. And then we want to cast it to I16. As I64. I64 as I64. Normally you want an envelope to ramp up and down, otherwise the first random sample is a sharp change. Yeah, I mean, because we're generating random noise, right? The first, whatever the first time signal is, suddenly has a bunch of volume. As a result, the speaker has to like blast to hit a sharp edge in the audio spectrum. And so that start is going to be severe. So we could apply fade in and fade out. We can do that. But that's boring. Okay, now this is way more reasonable. Let's go back to 12. All right, we're back to white noise. And is there still a... I don't hear the impulse as much anymore. Okay, you want to look at the print line. Sample.imaginary. Is there anything in there? There is stuff in the imaginaries. But we're just ignoring that for now. Okay. And then if we want to, if we really, really want to, what we can do is let mute dampen. Like if we want to fade in and fade out, we could do is trying to figure out how I want to do this. I think what I'll do is let's do like minus 100. And then we'll say that amplitude is how do I want to do this? Minus 1.0. And I want to say plus equals amplitude times dampen. And then dampen is dampen plus 0.1. There are fancier ways to do this for sure. Min of that and 0. Fine. This will actually be this guy. Amplitude. This is a real poor man's fade in. Why is it unhappy with me? Ah. No, I want times. That's not at all what I wanted. That's not at all what I wanted. I wanted this. Amplitude plus amplitude, which is really multiplied by 1 plus dampen. Right? I feel like that should work. So we take the amplitude, we add amplitude times dampen, which starts with minus 1.0. So that should be 0 amplitude. And then we increase dampen by a little bit all the way up to 0. When it hits 0, it'll stop incrementing. And so then amplitude will be amplitude plus amplitude times 0. Oh, but I have way too many samples per second for that number to be sufficient. There we go. Okay. Yeah. Okay. Beautiful. Your complex signal needs to be symmetric if you want to get 0 LM imaginary component. Imaginary is not 0 since when you start in the frequency domain, the spectrum has to be anti-symmetric to get a real signal. This happens automatically if you start with a real signal. Right, but we don't start with a real signal. And so therefore, the imaginary part is non-zero. But that still makes me think we should be using the norm here. But I guess because it's random noise, it doesn't matter. But regardless, this is clearly white noise. Sounds exactly like white noise. So we successfully have white noise. So now I'm going to argue we successfully have white noise. So now the question is, can we make pink noise? The frequency spectrum of pink noise is linear in the log scale. It has equal power in bands that are proportionally wide. This means that pink noise would have equal power in the frequency range 40 to 60 Hertz, as in the band from 4,000 to 6,000 Hertz. Since humans hear in such a proportional space, where doubling of frequency is perceived the same regardless of actual frequency. So every octave needs to contain the same amount of energy. Interesting. Density proportional to 1 over F. So I think we can just compute that, right? If the density is proportional to 1 over F, then we can just compute that here. So what we actually need is we need to start looking at what we need to start doing some argument parsing. Noise is none, or kind is none. Then we're going to match on std and args nth 1. 0 is the name of the program. And if we get brown, if we get white, then something. If we get brown, then something. Brown is to do. Actually, anything else is to do. Kind noise not supported yet. So for white noise, I think what we need all of these to be are functions. So I think what I'll do here is actually pull this out and say that this is going to be a noise, and it's going to take... Ooh, how are we going to do this? Spectrum setup is going to be an FN mute of a mute of complex of F64, right? So it gets to change the spectrum setup for each block. And for now, that's probably good enough. And then this is going to be noise of spectrum. And that's going to be simply this. And I guess we'll give in the RNG as well. Okay. So this will now say spectrum setup will be given the RNG and a mute to spectrum. Oh, rand. Sure, let's call it RNG, why not? And it needs to be mute here so that we get to call it as an FN mute. That's fine. In fact, we don't even need to pass in the RNG because as an FN mute, we can now do this. We'll create the RNG out here. And then this gets to borrow the RNG, which is fine. Cool. And then this has to end with okay. And then pink noise, we don't have a definition for yet, but we will shortly. And now it's upset about something else, which is, some of this, some of this, some of kind, and none. Sure, none is white noise. Dot as deref, so we get it as a stir instead of as a string. And then this is upset because the closure is expected to take 2 arguments. We don't need the RNG anymore. And then this is upset because cannot find amplitude. Yes, because amplitude can also now come out of here. And this no longer needs to be this. And this is now RNG.random. And kind isn't being used. Excellent. Oh, you want to see the spectrum? Sure. Audacity. Oh, stop showing me this. Thank you. Audio wave. Looks a whole lot like white noise to me. Can I view it? Spectral selection. I was trying to see if I could... surely there's a way to show me the frequency analysis of this spectral. I don't know. There are audio engineers now debating in chat whether we should be using real or norm. There's an FFT in there somewhere. Okay, so right. So for pink, what we were saying was the amplitude should be inversely proportional to the frequency. And so iter mute dot enumerate. So this is going to be, yeah, this is like, this should really be max amplitude, right? And then this should be, this should say amplitude, because that's what we're actually iterating over. No, it's actually sample, I guess. It's not sample, it's, what do you call the constituent parts of the frequency domain spectrum? Frequencies? I get, maybe they are frequencies. Fine, frequency. But it should be the max amplitude, but it should be, oh, they're called bins. Aha. Thank you. For bin, we want this to be inversely proportional. Oh, to select spectrogram view, click on the track name. Click on the track name. Okay. Aha. Spectrogram. Ooh. But also not particularly helpful. Although, interestingly, not quite what I would have expected, right? I would have expected to be more uniform if it was white noise. This seems to have more amplitude in the Oh, what's happening? Oh, I see. I get to select like that. See, now someone's just making up words. If you don't make the spectrum Hermitian symmetric and take real at the end, you essentially divide the amplitude by 2. You divide signal power by the square root of 2. Interesting. I'll let them keep debating in chat exactly whether we should be using real or norm, and then in the meantime we'll get some stuff done. So this is suggesting that it's simply a 1 over frequency. That feels like it's probably not true, but we got to start somewhere. As F64, let's just see what that looks like. So in fact, let's open the audio waveform now. Let's see if it looks different. Spectrogram. It does. Does it sound different? Pink dot. It shouldn't, because I didn't pass in the argument, so of course not. White dot wave, and then I will cargo run pink. Move audio to pink dot wave, and we'll play pink dot wave. That makes no noise. So that feels incorrect. But the amplitudes are going to be off here. Because with pink noise, I feel like the amplitude has to be higher. Because we're adding the slope, you end up with very little energy on the higher frequencies. So I think the max amplitude probably needs to be per thing. So if this, let's say this was 128. Yeah, there's something here. More. Okay, this needs to go away. But that doesn't sound like pink noise. If anything, that sounds like brown noise. Oh yeah, we are dividing by 0 here, aren't we? For FFT, its main toolbar, analyze plot spectrum. Okay, so back to waveform. And back to waveform. So I select a bunch of stuff. Main toolbar, analyze, plot spectrum. Aha! Oh. Well, this is interesting because at the lower ones, yeah, with a linear frequency, they're straight. With a logarithmic frequency, they're not. Huh. Why? This is for the white noise, by the way. You should convert frequency index to frequency. After midway, the frequencies become negative. Oh. Right, because this is the... this is the part where we could also just go to samples per second divided by 2 plus 1, right? Why am I not allowed to index this? Oh, as use size. Ooh. Why did that noise suddenly go up so much? Oh, it's after the dampening stops. That's weird. Oh, you're right. Hard to analyze low frequencies because it's the average over the track length. There's only 10 waves of 1 hertz in the file, right? Because a 1 hertz signal is 1 second long. And so 10 seconds, you only get 10 of them. But why? Like, okay, this is going to be loud. So let's make this be down to 8 maybe. It gets louder and louder. When I only go across half the spectrum. Someone said in chat that the frequencies go negative once you go past the halfway point. Yeah, I mean, ignoring pink for now because I think that the scaling by hertz here is probably too strong. This needs to be something else, but even for white noise, like, okay, let's no, I don't need to save that, but thank you. So let's. Whoa. Okay. Well, I think I see the problem. Plot spectrum. But okay, so we have way higher volume in the highest, but why did our white noise changed? Because spectrum is set to 0 all the way through. And now we changed to only set the first half of the bins. And then we get this property. Why are there negative frequencies and why does it matter? FFT, negative frequencies. Let's see what the internet can tell us. Ha! Why are there negative values in the output array? The second half of FFT array is the conjugate of the first half. So it doesn't contain any new information. But we are not filling it as though it is the conjugate. So how should we fill it? I see. So what this actually means is we need to set, can we simply automate this down here and say, can we simply down here do this and then do posneg is spectrum dot split at mute and then give in the positive things to here, and then for bin in the negative, mute.enumerate set bin is, can I simply negate pos of I? No, it's the other, it's at least based on this. Yeah, you get minus the next one. This is where the made up words become important. Yeah, I know, it's true. I see. So the output here is it's mirrored at the center. So this would be, it would not be I. It would be the negation of pos.len minus I minus 1. Real parts mirrored, imaginary mirrored and negated. Time for gamifying the off by 1 error. Yeah, I know. Oh yeah, that's the other way to go to do it, is to say, I see, instead of enumerate, we could zip with pos iter rev and say that this is simply then this. And it's not just negation, someone said. It's the conjugate, yeah, okay. And am I right that this is the split at? Like, what's the setup for split at mute? It's, yeah, so pos will contain everything up to but not including the +1. And then the negative will contain everything following. And I think that matches this too, right? So yeah, I think that's right. And now the belief, right, is that assert eq sample.im, or assert sample.im is complex, no, is 0, right? That's the belief. One bin will not be mirrored. That is the 0 hertz bin. Yeah, which is fine because we're iterating over neg here, which will then have 1 fewer elements, right? It's unhappy with me because it does get imaginaries. Yeah, it won't be exactly 0. It'll just be small. But it's not, I mean, it's 5. How about we say it should be less than 10? Otherwise, print out sample.im. How's that sound? 10 sounds like a very big number. 20 sounds like a really big number. 32 sounds like a really big number. 64 should be a really big. I think you're a lion. 256 Oops. 256. Yeah, it's not that small. Okay, so that means we've messed up here. So I think this means we're off somewhere here. Let's try +2. No. Let's try not +1. Oh, this should not have this anymore. This should now just walk over spectrum. But it shouldn't set the 0 hertz one, although it doesn't matter what it's set to because it's 0 hertz, so it has no waveform. So arguably here we could pass in, actually maybe that's a good idea. We could do this. So we spit at that +1. We skip out the 0 hertz bucket. But this should still be right. Oh, the 0 hertz has to be real. That's fine. So we say that to be 0. But something's wrong. Split out mute samples per second. So this is 44.1 thousand divided by 2. So that's 22,050. +1. But if we think of it as, I think it shouldn't have the +1 because of the 0th index. And I think the Poslen Neglen. Yeah, because now they're the same length. But the next thing that now gets weird is that the last negative entry now ends up being the conjugate of of 0 hertz. Is that right? That doesn't look like it's right. It should be the conjugate of this guy. Yeah, so we're iterating over pause, going from 0 hertz to 22,000 hertz. And then when we go over 22,000 hertz, we go to minus whatever, 44,000 hertz. But that, what should that be set to? Because that can't be set to the conjugate of the one before. It makes me wonder if this is like this skip 1 and that neg0 also needs to be set to 0. Yeah. Now how small are they? Yeah. Is it less than 2? Is it less than 1? Yeah. Is it less than 0? It's not less than 0. It's very small. Great. Okay, this makes way more sense to me. And see, I got it without knowing audio. Well, kind of without knowing audio. Okay. Yeah, because this one, neg0, if that's minus 44k, first try. If that's minus 44k, it doesn't make sense for that to have any amplitude to it because you can't represent it in the signal. At least in my head, this makes sense. This makes more sense now. Okay. And in fact, maybe this one doesn't matter. Yeah, so it's the skip 1 that matters. Is that the conjugates get set after that one. I think this one also realistically probably does not matter. But let's find out. So if we run this, neg 0 is 22,050 hertz. No, it should be negative, right? Otherwise we've messed something up. Are you saying this should be +1? And that this should be 0? I don't think that's right. I think this is accurate. It's because we removed the +1. Okay. I'm worried about the volume now. What did we set the volume to? 8? Okay, that's been our friend in the past. That sounds pretty promising. Okay, all of this, analyze, plot spectrum. That seems pretty white noise to me. Okay, and so now, if we move that to white, and then for this pink, let's go back to something less. It did say for pink noise, decreases by 3.01 decibel per octave. Density proportional to 1 over f. But that doesn't actually mean it's 1 over f, right? It's just proportional to 1 over f. Power density falls off at 10 decibels per decade. Okay. An octave is the interval between notes, which is twice the frequency of the vibration of the other. Okay, so each doubling of frequency should have 301 decibels, which is a logarithmic scale, less power. So every time we double the hertz, we should have the power. But that's what you get if you do this, right? This one's already, if hertz doubles, then amplitude halves. Or is it power or is it amplitude? Pink noise. the power density. Right, whereas what we are setting is amplitude. And someone pointed out that power, amplitude should then be proportional to 1 over the square root of the frequency, because power density is proportional to amplitude squared. Okay, so then this should be square root of this. But the hertz here, so this is actually not quite right. Because this should be +1. And we want this as F64. Pink. I hear something, but it's not very loud. I hear something, it's still not very loud. 64, dare I? 256. Does that... That's ours. And this is Wikipedia's. Those sound pretty similar to my uneducated ears. Let's go ahead and open that one. Well, that's a wonky signal, but that looks pretty good. That looks pretty good. That arguably looks way nicer than white noise does. Okay. Okay. So we move that to pink.wave. So now I guess let's do brown. Actually, let's figure out how do we compute this. So with pink noise, it's like, if you look at like area under the curve as total power, then this will be if we go halfway through the well, but that's halfway through the frequency spectrum. If you go halfway through the frequency spectrum, so at like so that would be, sorry, halfway through the bins. If you go halfway through the bins, you would end up at like 10 kilohertz-ish. And there we would have we would divide by the square root. We would be dividing by the square root of, so about 105. 8 times 105? That doesn't sound entirely implausible. So I think here's an interesting question. Like if we pull this out and say max amplitude is 8, and we say here our max amplitude is actually, or maybe we should say average amplitude is maybe more accurate, right? We want here the max amplitude to be the average amplitude multiplied by the square root of 22,050 divided by 2. What? Why is this ambiguous? F64 F64, F64. How? I don't understand how this is an ambiguous type. Oh, it's because we're picking up squirt from complex numbers or something? Yeah, we're picking up from other places. That's not what I want. Do I have to like F64 this one? So now those sound like roughly similar in volume to me. So if we now do, if we open white and then we open pink, I mean, they're not equal. Can I set this to show me? Like, can I? Aha. It's currently linear in amplitude. If I zoom into this and I zoom into this, is there a way for me to like zoom into the amplitude? Because that's really what I want to do. Ah, zoom in. Zoom in. They seem like kind of aligned now in terms of amplitude. It's obviously not perfect, right? Because it also depends on our perception of volume, which varies by frequency. So the scaling won't be quite perfect, but I think this seems to be about right. So let's then do brown noise. Yeah, for the feel, you probably want decibel, I agree. But let's do brown. Okay, back to colors. Brownian noise. Oh, sorry, Brownian. Brownian. I wish it was a Brownian walk kind of noise, but it's not. Is noise with a power density which decreases 6.02 per octave with increasing frequency. So frequency density proportional to 1 over f squared. It's also called red noise. I see. So this one is even more aggressive about suppressing the higher frequencies. Oh, it does mention random walk. Brown noise is not named for power spectrum that suggests the color brown. Rather, the name derives from Brownian motion, also known as random walk. But how does it relate to Brownian walks? It doesn't say. Why doesn't it say? Okay, but to f squared. Interesting. So actually, when we previously thought we were generating pink noise, I think we were generating brown noise. Because this squared would just be this, right? And now it would be divided, multiplied by this, which terrifies me. That sounds like a very high amplitude. It's related to a Brownian walk because at every sample you take a random step up or down to get the next sample. Oh, you're saying if you did that, you would end up with noise that looked like this. Because we are still generating random samples here. 6 dB is 1/4 of the power, so it's 1 over square 4. It's 1 over the frequency squared. And the relationship between frequency and power density let's in fact, someone posted it further up, right? That let's write down the rule. Power density is proportional to amplitude squared. Also, I can't spell. Proportional. So that would mean that if the So that means the amplitude is the square root of the density. And now we want the density to be divided by the frequency in hertz. So divided by f, which is where we get square root of 1 over f. So 1 over square root of f. That's where we get that modifier from. But if we now want this to be density over f squared, then wouldn't it just be this, right? It would just be 1 over f. Yeah. So it's not, yeah, okay. So it is this. Which is what we originally did for pink noise. Yeah, so our original pink noise was brown noise, or Brownian noise. Instead of converting from polar, could you multiply by random scalars of I? Oh. Yes, we could, actually. That's a good point, because when you... So let's take a look at this. So complex number multiplication. So when you multiply complex numbers, no, that's not what I want. I want this. So if you multiply by I, you're actually rotating the complex number. And so what that means is if you multiply by, so we couldn't just multiply by a real number, like by a scalar, but I think you could multiply by a scalar imaginary to rotate to basically an arbitrary amount. And so if we picked a random number and multiplied by that much I think you'd be rotating, which is effectively changing the phase to be random without changing the amplitude. And so that way we wouldn't need to go back and forth between the... that way we wouldn't need to go back and forth via the polar coordinates. So we could then just generate the polar coordinates once. In fact, we could just generate them with a face of nothing. I is always by 90 degrees. It's e to the power of the scalar times I. That's right. In which case, I don't think this saves us very much. So I think I'm going to leave it the way it was. Okay, so I think that means we have Brownian, right? So if we do Brownian... That sounds wrong. Oh, that's because for Brownian, our amplitude is way off. And that's because our scaling ends up wrong here. Why does our scaling end up wrong? because it goes to 0 so fast, I think. Like if we did this and do 1,000, let's say, and do this, so we get some clipping in there. But is that because of... I think it's because we end up... Interesting. What are those impacts from? Because this does sound like brown noise. Like if we go back to here and we play brown noise. That sounds right. Yeah, and someone's pointed out the problem is probably that the lowest frequency component, like the 1 hertz component, it has so much more volume than the other ones that whenever it hits, it ends up peaking and then you get that click. But I wonder why that doesn't happen here. And I wonder if that's related to the angle of the slope here. So I wonder if you could make this better. Oh, it's almost, yeah, someone, I think you're right, that it could be one of two things, right? It could either be because of the 1 second binning. And so if we, the 1 hertz signal, now that we're starting with a phase, doesn't start and stop at the boundaries of the 1 second. It might start at like, half a second into it. And so it's actually at max peak when we stop the 1 second, and then we just restart it at a random point in the phase, and you get these weird like steps. So that could be one part. The other could be that the 1 hertz signal ends up being such a big peak that we actually clip whenever it occurs, and so you get these sort of sharp things where you don't actually get the right frequency. So one way to deal with this is, for pink noise it was okay, but someone pointed out too, just skip over the first, like the very lowest hertz. Ship. Well, that sounded completely wrong. Yeah, attenuating the lower frequencies is the other way to do it. Make the intervals 1. Make the intervals 1.1 and overlap. Oh, so they don't perfectly align with the... yeah, so they don't perfectly align with the wavelengths, maybe. Feels like there should be a cleaner solution here. Because the other option, right, is to blend, but that feels like it's a... Now the negatives are not computing to 0. They should, because we still have that assert in there, that the imaginary part stays under 1. Yeah, I mean, if we now open this file, like, look at this. What's happening here? Because what's particularly strange here is that the... Wait, why does this start at 1? What is happening here? Could it be that we need to clear the output array? No. Do we need to clear the scratch? No. No, we're not in the musical mode anymore. Like, what happens if I plot the spectrum of this? Linear frequency. Log frequency. There's no internal state in the FFT, I don't think. That's why it has the scratch, for example. And we... now set nothing for the first 20. Does the scratch need to be reset? Let's go read the docs for this a little bit. Divides input and output in what? Divides input and output into chunks of size self.len and computes an FFT on each chunk. Oh, I see. So if you can provide inputs that are longer than the chunk length, than the length you set for the FFT, but if so, they'll be processed separately. This method uses both the input buffer and scratch buffer as scratch space. So the contents of both should be considered garbage after calling. Oh, okay. So we cannot reuse spectrum, but we reinitialize spectrum anyway. Interesting. So then we're actually fine with this being in place. There's no real reason for it to be out of place. So we can get rid of this and then say process in place. Yeah, and now, okay, yeah. And we're now skipping 20 of them, so we're not reinitializing them to 0. That's definitely the problem. So a couple of things need to change. So this needs to be in place scratch now. In place scratch. This is now going to be spectrum. And they're the same length, so that's fine. And then the challenge is going to be that this has to set all of them. So for bin in spectrum 220, bin has to be complex 0. And same thing here, because otherwise they end up with garbage. That sounds a whole lot more pleasant. And now if we do this... Okay, so that's still peaking. But that sounds mostly pleasant. I heard one click in there. It is interesting that this formula doesn't work. Like this made it way too loud. It made it clip. But why? Because this doesn't sound that loud. Right, but if I make this 10K, you occasionally hear the clicks, which whoa. Oh yeah, because we skipped the first 20 hertz. And it basically goes to 0 at like 10,000 hertz. So I wonder if the... I wonder if this needs to be divided by 4. I think that's actually right. Like, volume-wise, I think those are about right. And I think it's because, as someone pointed out too, the amplitude here is linear, but volume is logarithmic. But in any case, this seems okay for now. I'm fine with that. I don't know if you can beat the clicks by just skipping the first 20 bins. By random chance, the bins might be really high at the end of an interval. Yeah, that's what I'm thinking too, that the clipping is probably not because of the 20, but because of the edges. But the edges do get worse with the longer waveform, I think. And so there is an interesting question of how do you blend, if we sample this in 1 second intervals, how do we blend them better? I wonder if one option would be that we don't fully randomize the phases, but instead... So we could crossfade or something, right? But the other option would be that we simply, instead of changing the faces completely, we just randomly walk the faces slightly. Right? In fact, does the face even need to change? I guess if we want the signal to feel kind of dynamic. So then here's what we could do. So we could actually pass in the interval, like which interval number it is. Actually, let's do that as the first argument. And then I and I. And then we could say if I is 0, then this. Otherwise... Oh, but we can't do that because spectrum gets overwritten. But there was a process immutable while keeping input untouched. So that would let us... Okay, I think that's the thing to do. I think we change this. Yeah, okay. because that also means we don't have to reset it every time. So we go down here, we say this is going to be get immutable scratchlen. Mutable scratchlen. And actually this can now just be new because this resize is going to take care of that. And then here, this can now become process immutable with scratch. But now we need the output again. That's fine. So that's going to be this. That's going to be mute time in time. This is now read-only version of Spectrum. Y is duration in second to U32. Sure, that's fine. It can be U32. Yeah, we're basically doing a Brownian walk of the phases of the frequencies. And so now here's the other thing that's interesting. I think this doesn't depend on the type of the noise. So I think we can actually do this, which is kind of cool. So all of these are just going to not get an I. And instead down here, we're going to say, if I is 0, then this. Otherwise, and the conjugates probably still need to be computed every time. If the interval is 0, then we call the setup thing. Otherwise, we walk the bins from we walk all the bins, and then we and then we want to rotate the why does it not give me why is pos now considered immutable? Sure. Bin dot and this is where we need to use the trick of rotating complex number. And we just want to rotate by a random but small amount. No, that's not what I want. Yeah, so this is one way in which you can express the a complex number or any xy coordinate. And this is the polar form. So it's the radius times e to the power of I and then an angle. And it's the same thing for this one. So that should mean that we should be able to do bin and multiply it with, does complex have an exp? As it does, which is e to the power of. And then here we could say complex from polar. Can I make a unit here? No, okay. Of 1 and a random but small angle. mute RNG is rand RNG. RNG.random. Because we want to add we will rotate it by a very small angle. So how much is a small angle? Oh, for next we only want the imaginary component. Yes, you're right. So this should not be that. It should actually be the real of 0 and imaginary of this. But it's not between 0 and 1 because this has to be in radians. And so how much would we be willing to rotate the phase by? And remember, this is from one 1-second segment to the other. And so this could be, I mean, we could do like, why is this being unhelpful? Consts frac pi 8. That's the smallest one we have. That's pi over 8. So it's anywhere from 0 to pi over 8. This has to be F64. Thanks, Clippy. Okay, so I think this should mean we now set up the noise by setting all the amplitudes based on what the sort of scale tells us that noise should be like. So the frequency to amplitude, and then we randomize their initial phases, and then over time the phases will drift of the different frequencies, but they will drift by small amounts for each segment. So then they shouldn't. There shouldn't be very severe clipping at the borders, I think. MPV brown. MPV. Isn't exp pi times I times theta the same as just creating a from polar with radius 1 and theta? That's probably true. So I suppose we could do this. And I think that's the same thing. Yeah. No, that's pink. I didn't hear any clicks. That sounds pretty good to me. It seems maybe too loud though. I think the other thing is like, is it repeating, which is very, very hard to tell from this. If I do, add monotrack. I take 3 to 4. No. Add monotrack. And we put this guy under here. then we zoom in. It's very hard to say, but are these the same? Remember, they should be very similar, but I don't think they're the same. Right? But they should be similar. They just shouldn't be identical. So let's take something from like the end, right? So let's do like, I guess 4 to 5 as best as I can. Because they should drift more the longer the thing goes on. Like, look here, for example. Like, even if we say, okay, this aligns with that probably. Right? Like, this. We zoom in even more. Like, these are clearly not the same. Like, let's say these align. I don't think these align at all. Maybe this looks like it like used to be the same, right? I think this worked. I'm going to claim this worked. If the signal repeats every n seconds, then the spectrum of the entire thing should have a peak at 1 over n. Let's see. Undo, 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 undo. Analyze, plot spectrum. I don't see any significant peaks here. I think that worked. I mean, we can also Brownian.wave. I think this is fine. We could make it rotate more, right? But if we do that, then we'll have more of the clipping. Yeah, you get more of the tears at the edges of the intervals. And I mean, we could rotate them by even less to get less discrepancy. We could even rotate them not at all, but then you get the... That's very clearly repeating. Like, you can hear the same, like, pattern happening. Whereas with this... Oh, I don't know. That sounded kind of repeating to me now. Oh, man. Now I feel like I'm just like slowly but surely losing it. Okay. Someone keeps suggesting audio envelopes. FFT. Can you rotate an amount proportional to the frequency? I mean, I suppose. Yeah, because I guess the lower the frequency, the less we're willing to rotate. So we certainly could do that, right? Because we could also multiply by the hertz divided by 2250. So that way we'd be, the higher the frequency, the more we'd be willing to rotate. So if we did hertz bin in pos itermute enumerate I guess skip one as of 64. So this would scale the rotation such that only the highest frequency we're willing to rotate by a full pi over 4. But it's hard to tell, right? Because if we now have like a 20 hertz signal, and we're only willing to change it by a tiny amount for each second, then even a 10-second clip, you might not hear very much actual rotation. So maybe now we should be willing to rotate by more. Now we're just trying to find patterns in noise. I don't think we're going to get a whole lot farther than this, but this feels about right. Okay. So now we have Brownian. Let's maybe add one more before calling it a day. Rotation limit could be based on power. It could also be based on power. Although for all of these, right, the power, most of them have power that's inversely proportional to frequency, so those end up being the same. But for blue noise, that's not true. And so for blue noise, actually, this might make more sense. But let's go ahead up here and say, let's add blue noise. So blue noise is going to be, blue noise power density increases by 301 per octave. Okay, so it will be more like pink. But it will be not divided by rotating a bin's face at a constant speed will move the bin's center. We're not rotating it at a constant speed. We're doing a random offset. So for blue noise, we want the frequency to increase. Do we simply multiply by the same number? I think we do. This still ends up being that. No, it's still divide by, but it ends up being. We need sort of a 1 minus here. We need a. Yeah, we need to divide by the inverse. So we need this. Dot squirt minus that. Which is F64 squirt because of the trait that gets brought in. Oh yeah, or we could just reverse. No, reversing the iteration doesn't work. We can't just iterate backwards because the... Oh, I see what you mean, because the hertz... I see, because we would reverse the iterator, but the enumerator would then go from the back. That works too. Okay, sure. Well... But this feels nicer though. Right? It's the same thing, but iterating over these backwards. So if we did rev is there an R skip? No, there's not, is there? We would need a dot skip 20 rev enumerate. Yeah, that ends up right. So if we did this version, like this isn't really hertz, right? It's like I guess it's inverse hertz. Yeah, I guess we don't need the skip because the low frequencies get reduced by so much anyway. Or they end up with low volume anyway. Sure. All right, fine. Yes, but now we might end up with really high volume for the high frequencies, but that might be okay. Because I don't think it's as much of a problem for the high frequencies with the clicking, because they repeat so frequently that I don't know you'll even notice the switch of phase. But let's find out. Blue. Okay. It's not as loud. Doesn't seem quite right. Feels like it should be even sort of steeper, right? Yeah, let's plot this guy too. That certainly doesn't look right. I don't think this is right. I think the... No, but it should be. So we have the same scalar factor as in pink. We enumerate from the back. And so that would mean that the highest bin gets the same modification as the lowest bin did in pink. .01 decibel per octave with increasing frequency. 3.01 decibel per octave. Spectral power density reduces. Huh. So here we end up with 1 hertz, well, 20 hertz, ends up with an amplitude of the max amplitude divided by square root of flannery plus 1. Here, we end up with 2250 hertz. Gets that same amplitude. And then as you go down in hertz, you divide by a larger number. And the square root here should mean that in the logarithmic plot, you should see a straight line. We can't put the enumerate before the rev because then this computation is the same as the one for pink noise. What was the power density increases? 10 log 10 of 2. So 301 decibel per octave. So the density is proportional to F. I think I want to write this without the rev. I think I want to write this as enumerate. And this now is hertz again. And what we want here is for this to now be proportional to, right? Rather than inversely proportional to. I think it's just this, right? Like, okay, without playing this file, but just, whoa, okay. Yeah, because this ends up way too loud. No, wait, the power density is, not the amplitude. So I wonder if it would be easier to do this in power density in the first place and then convert back to amplitude. Because currently we're doing it in amplitude, but the adjustments are in power density. If we instead said, let's do it just for blue, I guess. So power, what did we say? Power is the, so average amplitude, is it amplitude squared or amplitude squared? I never remember. Someone wrote earlier up in chat, but I can't find it now. Let's see. Ratio between amplitude and power density. Power is amplitude squared. Okay, great. Right. And then we want the amplitude to be proportional to, the power should be proportional to the frequency. So this should be power times the frequency, and then the square root of that to get back to amplitude. Now the adjustment here is wrong, but yeah, it is gonna be hard to, I think, set a normalization between these. I think you're right. It just feels like it should be possible, but like I don't really want to give it up if I can avoid it. But let's see what happens if I do this and open this. What do I get? It's still, no, that's, well, now we just made it directly proportional to frequency, which might be too severe. Like, it would mean you simply need a factor in there, right? It would still be proportional. Which would be because, oh, because this Yeah, it's not really max amplitude anymore. It's like an adjustment factor, but it's not max. Yeah, that sounds a lot better. It's just, yeah, there we go. It's just mislabeled as max amplitude. So there we have blue noise. Yes, this isn't really a max amplitude. So this is mislabeled. And I do think it's easier to operate in this domain because then we can do here. So this is going to be like adjustment factor, or it's really a normalization, right? So it's going to be that times this normalization power 1 normalization divided by this, and then square root to get back to amplitude. And this is going to be, no, this is going to be power. And then here, normalization is going to be oh yeah, I guess you could also just, you could add up all the frequency bin amplitudes. That's also true. And then normalize. But I think here, actually for Brownian, we can just keep it the way it was. But for pink, it's not, it's a normalization factor. It's not actually the max amplitude. And same thing here. This is normalization. As if I now do this and do pink. Ooh, that was loud. Why did that change anything? Oh yeah, no, this needs to be, this is still in amplitude, so this needs to be this. Yeah, okay. So this is now pink. This is now blue. All right, so let's all settle down. This to brown, this to white, and then let's check them all. All right. So this supposedly, ooh, why is Brownian so loud? Okay, so the Brownian normalization feels not quite right, but okay, so white noise should be, what? Wait, no, this is blue. Yes, it says right there, blue. Okay, so analyze blue. Blue is blue. Sweet. Brown, analyze. That's brown, and we're skipping the lowest 20 hertz. This is pink. Pink is pink. And I guess, okay, if we're going to be really pedantic about it, right? So Brownian, affect, analyze, plot spectrum. And then here, pink, analyze, plot spectrum. So for this over here is pink, this is Brownian, right? And if we look back to the Wikipedia one, Brownian should decrease much faster than pink. And if we look at this, Well, kind of. Yeah, so in pink, so this is at the very end, it stops at minus 72. Here it stops at minus 78. So like if we look at the volume around 440, 440 is like around here. We see it's minus 46, and here 440 is minus 53. But the brown is also that doesn't seem right. Like, why does the browning one start so much higher? It starts so much higher because of the slope. Yeah, so if it's going to average to the same value. But like, okay, let's do 1400-ish is minus 56 is 1400. And this one is... But that's the thing, pink is quieter at 1400. And I expect it to be louder because it should be less sloped. So if we do linear frequency. Well, it's hard to tell because their scales are off from each other, right? But this doesn't seem quite right. Yeah, it's minus 3 decibel per octave for pink and minus 6 decibel per octave for brown. But I don't think we're getting... Okay, let's take an octave in brown, right? So if we go from 110 is minus 34 to 220, oh, is minus 40. So that is actually minus 6. If we do something else down here, like, okay, here, 1000 is minus 53 and 2000 is minus 56. So that is minus 6 decibels. If we go to pink and we do 105 is minus 47 and 210 come on, 210, okay, is minus 50. So that's minus 3 dB. So the slope is right. And maybe the brown is simply too loud. What's our normalization for the... Does this... Oh, this also has to be square root for the normalization because we're still normalizing the power. But then without the divided by 2, you think so? I'm not going to dare play these yet because... Oh, and I guess we should double check the white just while we're here. The white is... Linear frequency is white. Okay, great. Okay, and then let's open audio, which is the one I just generated for brown. This one's now too quiet. If I plot the spectrum, log frequency, that looks more like the steepness I would have expected. But now it's much too quiet. The reason for the divided by 2, right, is to get to halfway through the spectrum. So that one, it feels like it needs to be there for all of them. No, I actually think the previous thing kind of makes sense, right? Because the slope is so steep that for the average frequency to get the average amplitude, the low frequencies need to be so loud. But the reality is that in Brownian, the average frequency is like barely audible. And so the scaling is just completely off. It's almost like, there's an interesting question of maybe the thing to scale here is not the average, but the loudest. Right? So you want the loudest amplitude to be the same. Although that's weird too, because then harmonics wouldn't. I mean, we could do actual normalization, right? That's the other option. And maybe we should. But I think actual normalization would be the same, right? You would just scale everything to the loudest amplitude. Otherwise, you need to do something real fancy like computing like the sum of the squares or something and normalize based on that. Or we normalize in the time domain. But if we normalize in the time domain, then that feels weird too, because it would mean that, well, depending on the scale at which we do the timing, whether we the duration over which we do the scaling, if we do it over the whole file, then maybe it doesn't matter. But like scaling it by the amplitude that we happen to sample feels like it ends up wrong unless you sample over enough randomness. Yeah. Might be that we just kind of have to give up on having this like computed scaling factor and actually we need to do something more dynamic. But I think the other way to go about this would be to, at least for Brownian, which is very steep, to simply compute the actually, okay, how about we compute how loud is the loudest or what's the amplitude of the highest amplitude thing in pink, and then we scale all of ours based on that factor. It won't quite work because of human perception based on frequency, but like it feels like that's kind of what we're circling around here, right? So so pink normalization is that, pink power is that, and pink max amplitude is pink power divided by one square root. That makes sense. So that's the pink max amplitude. And here we didn't do actually, these cancel each other out. So this is the pink max amplitude. And then we should just do that. but we're skipping 20. It's also skipping 20. So that's not quite right. It's actually... It's actually this, right? So 20. That's the highest amplitude we'll have in pink. And we want... And we compute... it's like we want to take this value, which can actually be arbitrary. It can just be 1. And then we want to scale it such that the loudest one is the pink max altitude, max amplitude. Right, so it's like this. Yeah, so we're cutting off the high 20s. Yeah, it ends up weird because of the slope is so steep. But I do think here that what we want to do is simply so if Hertz is I could tell my brain is slowing down. If Hertz here is 20, right? So we'll skip 20, which means the first index we'll actually get is 20. Which is actually 21 Hertz. Then it really does feel like this should just be pink max amplitude, right? Because it's like 1 divided by this. Oh, but maybe, okay, but maybe we do actually need to normalize it. So it's that, but divided by this, which is our highest one, our loudest one, I mean. So that gives us a ratio. And then it's this one times pink max amplitude, so that the loudest one we end up producing is the same as the loudest one that the pink one ends up producing. "120 beats per minute." Well, that sure doesn't look right. But it is actually, because if you look at it, yeah, look here. They now start at the same frequency, but the Brownian descends much faster. So this is now normalized such that the lowest Hertz is at the same decibel level as pink. Yeah, but this is where what actually hits us is the area under the curve is so much higher here. So it has to be, we have to compute it based on area under the curve. Feels like the only way to actually do it, which means we need to, I think, compute the whole thing, pick an area under the curve that we want, and then scale all the values afterwards. Or, alternatively, simply say it's going to be 2x louder. Right? Or 4x louder. To do, normalize this by this and everything by computing area under the curve of amplitudes. Maybe of power density, and normalizing that to a particular number. We got it. Nobody touch anything. Yeah, you're not wrong. Oh yeah, these should obviously be samples per second. Actually, okay. Const max frequency is going to be a U32 is going to be 22 of 50. This is going to be max frequency times 2. This is going to be max frequency as F64. Max frequency as F64. Fixed it. All right. You know, instead of eyeballing, Brownian is 4x quieter than pink. Excellent. All right, should we do one more? What's after blue? Violet. Violet is just boring, but we can do violet so easy. Okay. Violet. Oh no. Oh no. Violet is the same as Brownian, actually. Except that this becomes blue normalization. And this becomes also blue normalization. And it's computed as this is divided by and this is now here. This is a I don't even want to think about what that normalization looks like here, because this is no longer a 1 divided by. It's just the same as blue. Let's ignore the normalization for now. But the difference is going to be that here oh, this has gotten so much worse now that we did the whole thing. We're not taking the square root to go back to amplitude. And now, of course, violet is going to be way too loud because it doesn't have normalization. Yep. So just like for Brownian, the normalization now has to be divided by 4. Is that right? Perfect. Yep. Great. And if we analyze plot spectrum, that looks like violet. So it goes from, let's pick some random point on the scale. Goes from here, which is 25 is minus 86. And what? And 5 is minus 80. That's not 6 decibels per octave. Right? This seems almost too steep. Like, okay, what about here? This is, okay, 3. I need more zoom. But I want zoom in this direction. Why can I only zoom up and down? Okay, here. So this is 2000 is minus 88. 2001 is minus 88. 4002 is minus 82. Okay, so that is 6 decibels. Okay. Great. So we have violet. Then we can do one more. We can do gray. To psychoacoustic equal loudness curve. Oh boy. Oh no. But arguably, this is like what we need for normalization, right? Like, okay. Gray. Gray noise. Equal loudness contour. A mathematically simpler and clearly defined approximation is pink noise. An equal loudness contour. Oh no, it means we have to encode like an actual model into our thing. I don't want to put an ISO standard into my thing, but this is the A curve. Is applied to the amplitude spectrum, not the intensity spectrum, of the unweighted sound level. Okay. This is math. Okay. All right. Okay. We can do this. So for a given frequency, so for each frequency, RA is 12194 squared. Great. This is math I can do. Squared times the frequency in hertz, I assume. Okay, to the 4th power. Gotcha. No problem. Divided by hertz. It's hertz SF64. Let's make this easier on ourselves. Hertz power I2 plus 20.6 power I2. Okay, of course. Yep. See no problem. Multiplied by the square root of something multiplied by Hertz pow I2 plus 12194 squared. Okay, so there are definitely some numbers we can reuse here. F64 squared. I really want my square root functions back. Can I get rid of the... No, I can't apparently. Okay. And then we haven't figured out this yet. F64 squared. This has to be multiplied by this. And this is Hertz.pow I2 plus 107.7 squared, of course. Hertz pow I2 plus 737.9 pow I2. Okay. Why is it ambiguous? Oh, it's because I brought complex into the world. I don't even know what this is going to be yet, so that needs to stop yelling at me. Can I write like F64 here? Okay. F65, that's a new one. Nope. Nope. There we go. F64. 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 Okay. So that's RA. And then let A is, I'm sorry, what? 20 times RA minus, no, dot log 10 minus 20 times, okay, so we're gonna need, oh boy, okay, no, okay, RA is a function that takes a hertz and returns that value. Let RA hertz is RA of hertz as F64. Cool. Times RA of 1000, sure, dot log 10. This all seems fine, right? We're not worried about this. This is an F64. Yes, thank you very much. And then here we say RA 1000 is RA 1000. And this is going to be RA 1000. This one can go right in here. As RA. Perfect. I see no problems. Okay, so now we have this A value, which is approximately equal to +2. Great. And so that's the amplitude. I'm scared. Nan, good. Great. Oh. Okay, so we get nan out of our FFT, huh? Okay, good stuff. So debug this one. Actually, how about we just print line A and then we put it into dings. Okay, so it's that curve in amplitude, which doesn't feel like what I expected. Oh, the weighting function. But what is A here? I see. This is the gain in decibels, is what the A gives us here. It gives us the gain in decibels. And so if you apply that gain, then the middle frequencies should get louder. Right? These frequencies should get louder because this is closer to 0, which in decibels would be more gain, right? And this matches this kind of curve-ish, right? So why does that give rise to this curve? Because I would expect that expect the gain to be because the gain is higher in the middle. I would expect the amplitudes of the middle frequencies to also be higher. Oh, this is those sound louder. I see. Oh, this is the gain that we as humans have to them. Inverted. Yeah. Okay. So this is how we as humans hear them adjusted, therefore, that way. Therefore, we need to apply the inverse of this to the amplitude. To the amplitude that we want. The amplitude we want is the average amplitude. So our actual amplitude needs to be the average amplitude that we want. This is where I really want to use like UM or something so we get units on this stuff, because this is now in a gain in decibels. And the amplitude we have is linear scale. So we need to take But we're already taking the log here. So is it just then... Is it actually just minus A? That feels not right. But maybe it is right? I don't think it's multiply, because this is gain, right? I actually no, we need to, it's not the log. We need to take we need to do exp10, right? Like we need to do 10 to the power of A here. What? Well, why can't I why can't I use pow? Dot pow f. Okay, fine. That looks more right. But it doesn't look quite right, because this would mean we go to 0. Right? Because this y value ends up going like below 0 for the amplitude, which is not what we want. So this adjustment feels too severe. But it can't just be minus A. That doesn't seem... But why are these values all still positive? Like, average amplitude here is the number 8. So when we subtract A from average amplitude, how do we get 156? Positive. Like a positive number. Right? This is 8, right? And this is... There are too many bins. -9, yes. Oh, it's defined such that the average dB is 0. Yeah, which is not necessarily what we want here. Oh, it's because we're subtracting A, but A is a large negative number, is why. Yeah, so this, no, yeah, no, pow f. This is right, but it's just that this is normalized around 0 dB. And so what we would need to do is we would need to scale this so that it is not centered on 0. Right? Because, okay, let's, if we didn't do this, if we did this now, and then I close this, and then I open this. Wait, did I? Yeah. Analyze. Plus spectrum. So, so we end up with a pretty strange plot. It's like clearly there's something happening here, but it's not quite what we expected. I think R is the weighting that you can apply directly. Oh. Well, if that's the case, then I should be able to just say average amplitude times RA hertz as fx64. Ooh. Except that's inverted. Right, because I need to... I guess I could do this, but that doesn't seem quite right. I need to do... Right, because this is based on... This is based on how much louder it sounds to us. And so we need... No, but divide won't give us the right thing, right? Yeah, you end up with a enormous potential number here. I think what we actually need is it's like almost right, but I wonder... It's almost like I want like 1 minus, right? Like it feels like that. It's not right, but it feels like that. Right? It's not. Actually, it's kind of like that. But but I actually want the scaling factor to be... I don't want it to go all the way to 0. Ah, I see what's happening here. It is 1 minus this, but what I want to apply that to is the variation in the audio, not the absolute value. So I think what I would do is something like, you know, this divided by, this is kind of silly, but like this divided by 2 plus... this divided by 2 times 1 minus that. Oops. Because that way I'm offsetting the bottom so that it doesn't start at 0. And so I basically want to scale the difference between the... I don't want to allow this to scale all the way to 0 for things that need to be... that should be at sort of 0 dB compared to where they are. And so I think this is actually right. It's like... I guess actually it should be max. Right? We should be scaling by the... Instead of by the average, should be scaling by what we want the max volume to be. And the max volume... Yeah, and this is where we basically need the... this is where we basically need the root mean square thing we came up with, or we found. Now let's first... This guy can get a comment that says it's from here. But let's just see. So if I what does this play like? If I open this. I don't know. It sounds like a sound to me. Why are the low frequencies? I guess the low frequencies are always hard to sample, but like linear wise, that doesn't look terrible. This is a log plot, right? Yeah, so the log plot ends up kind of weird because you don't get enough samples of the lower frequencies. But we could fix that actually by changing the duration that we generate to be, let's say we generate 100 seconds. I'm not running in release mode. That's why it takes a while to... okay, audio. No. And then I run analyze over the whole thing. Still pretty noisy there, but like... And this still seems too high. Yeah, so the scaling here is still not... It's not quite right. Like debating what I even wanted to plot. Or what I wanted to generate. Maybe it actually is just average amplitude times 1 minus that. It just means that the or like 2 times that. Sounds kind of pleasant actually, but like loudness wise, it seemed pretty similar to the others. It is interesting to me though that the, like if you look at the Wikipedia one, see how the peaks, the amplitude peaks on the right are lower than the amplitude peaks on the left. And we don't really see that. Oh, actually, I guess we do see that here, right? Because these peaks are higher than this peak. It's just that they're sort of obscured by the lack of fidelity here. I wonder if there's a... Can I like... Hamming window. Hand window. Yeah, so like that goes to minus 60. But this goes to minus 61. So it does feel kind of odd. Although if you look at it too, like look at the difference here between this at minus 60 and this is minus 66. Whereas if we open, for example, the... let's take the pink noise, for instance. Right? And we analyze and plot the spectrum here. This goes from minus 42 to minus 69. And so clearly the actual range here is not very big. You know, I do wonder whether are the limits of the x-axis different? Let's see. This is... No, the x-axis seems to be the same. Minus 40 and minus 50 something. And for here... Minus 40 to minus... Yeah, no, the x and y axes are actually both the same on the Wikipedia ones. Although this might not be the same equal loudness curve as the one we're using, right? We just picked a random one of these curves. It's not clear they've been using the same one. So it could be they're using a B curve or something, right? In fact, do we know how to pick between these? Oh, I see. There are other frequency weightings that have fallen into disuse. Okay, so A feels like the one we probably should be using, which I'm guessing then is what's being used here. I honestly just changing this to window helped a lot. I mean, maybe it's just actually a matter of scaling it up so that the max lines up with what we got for pink, for example. Although this looks like it'll be real loud. Wait, but that made it... Oh, that's because I'm doing this wrong. No. Yeah, this should be 1 minus, and then this should be like 2 times. Okay, we don't need the insanely long file anymore, thank you. This can be, let's do 20 seconds, is probably fine. So if I go here, I do audio. Okay, and then we analyze this guy. I mean, it still looks about the same, right? Like these still go down pretty far. It's because the scaling here this isn't the right way to scale it, right? Like this is telling us, oops, this formula is telling us or really the one that actually gave us the A curve, right? So what was the, this was RA of 1,000. And then here it was A is 20 times RA of Hertz as F64 log 10 minus RA 1,000. Right, like this was the formula they gave us for actually completing the A, but this is the gain in decibels for human hearing at 0 decibels. And so it's like a discount you have to take to hearing a thing. So when we're trying to generate a signal, we need to sort of add the inverse of that. And so maybe it's simply, maybe it is simply the amplitude we want to have. It does feel like it should be just divided by the weighting. And then this feels like it'll just give really big values. And then there's some scaling factor to bring it back down. But at that point, it's really just 1.0 divided by It's 1 over that. You have to use a weighting formula in the frequency domain after doing FMT and just subtract the I weighting before the inverse. This is in the frequency domain. Like right here, we're in the frequency domain. And it's just before we do the IFT. But the thing that's interesting is, like, okay, let's say we do this. What if we clamp this at, you know, from 0 to, I don't know, 3 times the average? Or 2 times the average? Like, that curve is a lot more reasonable. It's still, it does look a lot more reasonable than this one. Spectrum. Yeah, that looks a lot better. But it still feels like we're clamping it too low, but like the louds are way louder than the rest. Right? Like if I look at this one, like look at the depth of that trough. How about converting the spectrum to decibels, subtracting the A curve, and then converting back? So that would be generate white noise, turn it all to decibels, then subtract because those are negative, that would end up adding. I don't think that's right either. I mean, you don't need to compute the whole spectrum first in order to do that, right? You should be able to do that right in here by saying this is the A curve in decibels for that frequency. And then what you're saying is the amplitude we want, so the average amplitude, in dB is the average amplitude is 20 times that dot log 10. Right? And then you're saying let target in dB is average in dB. No. Oh, autocomplete is being sad to me. Average in dB minus A in dB. And then A is going to be A is going to be F64 pow F of target in dB. Like so. Well, that's definitely not right. Target in dB divided by 20. But that's still not right. I mean, our average amplitude here is also stupid, right? It's just the average amplitude we set was just, it just happens to be the amplitude that we set the white noise to. So it's like, it's not clear that 8 is the right value, really. because that's just linear amplitude. The magnitude of the frequency component for each bin needs to be reduced by the equivalent frequency value from the awaiting function for that bin. Yeah, that's what we're doing here, right? So we're taking the desired amplitude for this bin, turning it into decibels, and then we get the A value for that bin, also in decibels. We subtract one from the other, and then we go back to amplitude, and that the resulting value is nuts. The question is, why is it nuts? And it's not... Okay, so fine. Let's then dot clamp from 0 to 3 times the average, or 2 times the average amplitude, just to clamp it to C. 3 times the amplitude. 4 times the amplitude. A weighting doesn't produce good results for less than 10 hertz. That seems right. Okay, so skip 10. Honestly, skip 20. Okay, do we then even need the clamp? We do still need the clamp. All right. So what do we actually get into this file now? If I now go here and open it, what do I get? Analyze plot spectrum. So this now peaks at... Okay, let's do 10, sure. Analyze. I mean, should I just not clamp it? That feels wrong, but what happens if I do? Well, I mean, it's not wrong. It's closer to the Brownian, actually. I think this is going to be loud if I play it. You know, I think that's just correct. It wasn't even that loud. Who knows if it's right at this point? It's true, but I mean, okay, reading through this, right? Like, this looks kind of right. Right? So we compute the A formula we're told in decibels. We compute the average we want in decibels. We subtract one from the other to compensate for the A weighting. And then we turn it back into amplitude, and that's what we plot. If we don't skip 20, let's do skip 10. Then we... Oh, I don't need the plotting anymore. I'm pretty sure there's some discontinuity here, that it's unhappy below some amount of hertz. Maybe there's a reason why the Wikipedia starts from 100. Could be. I mean, that's what happens then if we do that. Sounds fairly similar, but 20 seemed like it worked fine. You can hear like a kind of rhythmic thing in the background, which I guess is the low hertz things, right? Okay. I think this is a good place to call it. So we have an implementation of the WAV format. I'll put this on GitHub as well so people can find it afterwards, and you can play around with this and figure out your curves and make happy things from it. This can now go away too. We managed to implement a WAV file generator. We managed to figure out what the riff format was and how that worked. And we managed to implement a bunch of different types of noise. The normalization isn't quite there, but it's like, these are fairly reasonable now in terms of normalization, and all the frequency plots look right. So I think I'm pretty happy with where we landed. Now, I'm not going to claim that this is beautiful Rust code, but maybe you've learned something about audio. I certainly have. Maybe you learned something about file formats. I don't know if you learned a whole lot about Rust, but maybe you have. Or maybe you know audio from before in a different language, and now you know a little bit about what it looks like when you're writing it in Rust code. But in any case, I think we're going to stop it there. It's getting late. Thank you all for joining. I hope that was interesting. I'll see you in whatever the next stream is. It'll probably be another impl stream of some kind. I like doing these kind of streams where I build a thing and that it kind of works and I learned something in the process. Those are the best kinds for me. I don't know if it's good for you as the audience, but for me, those are the funnest ones. So cool. Thank you, everyone. Thanks for joining me. And I'll see you next time. And as always, to the people who watch live, thank you so much for being here. Not only has it been very useful to have people who know audio in the chat for this, otherwise it would be a lot more Googling for me, but also it makes it more fun to be doing these things when other people get to listen to the weird buzzing that I had to listen to as well and get shocked when the volume is loud. So I hope you have a good Easter weekend, and I'll see you whenever next time is. See you, folks.